அபி டோர் க்ளோஸ் பண்றியா? Okay. Good evening, everyone. Let's get started. Can you see my picture? I'm not able to see. Can you see my picture? Yes.
Yes, sir.
Okay. But I'm not able to see mine. Okay, fine. Okay. Anyways. Yeah. Let's have a quick review of yesterday's class. Yesterday, I mentioned that an amplifier not just has 2 ports for analysis. Practically, it has got 3 ports. And the third port happens to be the power port of the amplifier. And output always comes from the power supply. So it is the current from the supply that is being modulated in accordance with the input signal. So input signal is only for controlling, but from a small signal, you cannot get a large signal without a battery or without a power supply or without a VCC supply, so called, right? So output always comes from the VCC supply, right? So the output swing limits is always decided by the supply. So it puts a higher limit on the signal that you have to give. If your V0 is between minus VSAT and plus VSAT, then your Vin should be minus VSAT by gain to plus VSAT by gain. So that happens to be the largest Vin that you can give, right? And then I said it's not just the strength of an amplifier and impedance matching. We should also calculate the frequency reach. So how do you calculate the frequency reach of an amplifier, the bandwidth of an amplifier? The bandwidth of an amplifier is governed by something called tau, right? So you have to find the time constant of the amplifier, right? So to find the time constant, tau is always equal to R equivalent into C equivalent, right? So when you multiply, you get tau. And what is the bandwidth, overall bandwidth? The bandwidth is equal to 1 by tau. Now, what a single stage amplifier, if you see, it will have 2 time constants. One capacitor input, one capacitor output. So the order of the system is 2. But if you have 2-stage amplifier, 2-stage, you have a capacitor at the input, a capacitor in the middle, and the capacitor at the output. So 2-stage amplifier will have 3 time constants. A 3-stage amplifier will have 4 tau, 4 time constants. A 5-stage amplifier will have 6 time constants. A n-stage amplifier will have n plus 1 time constants. So the time constants keeps on increasing, but I told you there's nothing to worry if multiple stages are given. To find the bandwidth, all that we have to do is the total tau, the total delay of the system is equal to the delay offered by individual poles. So you take every pole, tau 1, tau 2, tau 3, tau 4, and add them, and bandwidth is equal to 1 by tau. So this is a simple way of calculating the frequency reach of the amplifier, right? And then I said, I've given you a symbol for an amplifier, and I said, how will you quickly solve, even by an approximate analysis, how will you quickly solve if a resistor is connected between input and output, right? If a resistor is connected between input and output, how are you going to solve? So last class, we mentioned that if a resistor is connected between input and output, or an impedance is connected between input and output, then this impedance can be replaced by two impedances. So you can just remove them for simple analysis, just remove, and you can connect two impedances. Z1 and Z2, right? And imagine this amplifier has got huge high input resistance, infinite input resistance. Now we are talking only about the gain and the impedance. So what sort of Z1 you have to replace here so that the Kirchhoff's law at the input side here is satisfied and the Kirchhoff's law at the output side here is satisfied. What is Kirchhoff's law here? The sum of currents that enter here is equal to leaving. So instead of the current leaving through Z, we want him to leave through Z1. We want him to leave through Z1 instead of leaving here. So we want to remove this Z and replace it with Z1. Then what should be the Z1 value? This Z1, we have found it to be Z divided by 1 minus V2 by V1. And V2 by V1 happens to be minus A, so it should be Z by 1 plus A. Z by 1 plus. Similarly, at the output port, we have found that this value Z2 is equal to Z by 1 minus 1 by V2 by V1. So it is going to be Z by 1 plus 1 by A, right? So if it is a resistor, it is R by 1 plus A. If it is a capacitor, then C equivalent C1 is going to be C multiplied by 1 plus A. At the output, it is R1 is equal to R by 1 plus 1 by A, and C1 is equal to C multiplied by 1 plus 1 by A, right? And inductors, don't worry, we seldom use them, right? So this is something called Miller's approximation. Miller's approximation. So Miller's approximation has its own limitations. The limitations is the gain that you're calculating is not with that impedance, it's actually the open loop gain, right? So slight error you will get, but still this is a good way of analysis because you can quickly arrive at the solution, right? By looking at the amplifier, you can assess the time constant. If you assess the time constant, then you can assess the bandwidth of the amplifier. I think this is where we stopped last class. Okay, I just want to close the door to avoid disturbance. Yeah. So this is where we stopped. And then I introduced op-amp as a basic abstraction, a basic black box. And I mentioned that op-amp is a high gain differential amplifier. It has got two input terminals and one output terminal, right? Why two inputs? So many reasons are there, but fundamentally, I told you the plus terminal is for voltage sensing or voltage summing, and the minus terminal is for current summing or current sensing, right? And op-amp inherently was a comparator. So it will compare V1 with V2. So we have seen this. I said V0 is A times of V1 minus V2. And even if V1 minus V2 is a very small number, a very large number multiplied by even a very small number, that's going to be huge, right? Because the power supply is hardly 10 volt or 12 volt. So what happens when V1 is slightly greater than V2? If V1 is slightly greater than V2, then V1 minus V2 is positive. This positive number multiplied by a very big number, the output is going to be the saturation voltage, plus Vsat or plus 12 volts. What happens if V2 is greater than V1? If V2 is greater than V1, then V1 minus V2 is going to be negative. Then your output shoots, it hits the negative rail voltage, which is minus Vsat or minus 12 volts, right? So this is the operation of a comparator, right? A comparator is going to compare V1 with V2, whether V1 is greater than V2 or V2 is greater than V1. Accordingly, the output, this is basically a digital circuit. The output is either logic 1 or logic 0, right? I think this is where we stopped last class, right? Now we will continue. Take down a gate problem. Calculate the duty cycle of the comparator given. Calculate the duty cycle of the comparator given. Right? Take your time. Calculate the duty cycle of the comparator given. This is a gate problem for 2 marks. Okay, so let's try to solve. I told you if the voltage at plus terminal, if V1 is greater than V2, then V0 is at plus Vset. So who is V1? V1 is the voltage at non-inverting. 6 sin t is greater than 3 volts. Your output is at plus Vset. Similarly, if V1 is less than V2, your V0 is at minus Vset. Or 6 sin t is less than 3, your output is at minus Vset. Am I right? Yeah. Now the threshold was 3 volt. The peak value is nothing but 6 volts, right? Yeah. Now just tell me, when does 6 sin t, what do you mean by 6 sin t? 6 sin t is nothing but 6 sin t is nothing but your input, right? V in. 6 sin t is V in. So 6 sin t is of the form Vm sine omega t. Omega t. What does Vm stand for? It stands for the peak. How big is the signal? And what does omega stand for? Omega tells you how fast the signal will move, right? It's the angular frequency. So omega here is 1. Omega is 2 pi f, or 2 pi by t is 1. So what is the time period? It is 2 pi radians. The time period is going to be 2 pi, right? So let me put 2 pi here, and half of it should be pi. Now the question is, when does this function, the sine wave function, cross 3? Sine t, 6 sine t should cross 3. That means your sine t is 0.5, or t is going to be pi by 6. So this is pi by 6. So what should be this point? In symmetry, pi minus pi by 6, that is 5 pi by 6. 5 pi by 6. Now, let us go back to the, as long as 6 sine t is less than 3, as long as 6 sine t is less than 3, your output is minus Vsat. So this line is 3. The portion below that line is less than 3. The portion above that dotted line is greater than 3. For all 6 sine t less than 3, the output is at minus Vsat. For all the portion greater than 3, the output shoots to plus Vsat. And for 6 sine t less than 3, the output is at minus Vsat. For greater, it's going to be at plus Vsat. So what is duty cycle? Duty cycle by definition is the ratio between the on time to the total time. The ratio between on time to the total time. So let me write duty cycle. Duty cycle is given as the ratio between on time to the total time. So what is the on time here? The on time is the difference between the 5 pi by 6 to pi by 6. So what should I write here? 5 pi by 6 minus pi by 6 by, and the whole period here is pi by 6 to 2 pi plus pi by 6. So this duration is again 2 pi. So this is going to be 1 by 3, 1 by 3 or 33.33%. Yeah. So what do you mean by, what's the significance of this, right? Duty cycle. What do you mean by 1 by 3? So it's simple. Because this is a comparator, if I impress this signal for 3 hours, 3 hours the 690 is moving, and here I connect an LED. Here I connect an LED. Here I connect an LED. So the output is high 1/3 of the time. So if I impress that signal for 3 hours, the LED is going to glow only for 1 hour, right? So the duty cycle tells you the ratio between the on time to the total time, right? So any square wave, you can, if it's an asymmetrical square wave, you can always define something called duty cycle. But if the on time is equal to off time, then if the on time is equal to off time, then we can say that the duty cycle is 50%, right? Abhi, if you shout, I'll kill you. Mama, close for our mic. Okay, so duty cycle is the ratio between the on time to the total time. Now, let us go to a very, very important application now. That is negative feedback. right? So what do you mean by feedback? Feedback means what? Feedback means you have to feed it back. You have to take a part of output and then feed it back to the input, right? Okay. So now we have a voltage divider at the output 1K, 1K. And we are feeding this signal back to the input. So let me explain you the voltage divider once again. So you have a V naught. This is a voltage source V naught. You have 1K and 1K. So what is V1? V1 is always going to be, or sorry, V2 is always going to be V naught by 2. Suppose if V naught is 5 volt, your V2 is going to be 2.5 volt, right? If V naught is 7 volt, it is going to be 3.5 volt. So this is a potential divider, a voltage divider. So V naught is a voltage at this point with respect to ground. So V naught covers both the resistors, but V2 is only across 1K. So half of the signal that is being backtracked from the output is manifested here. Only half of the total signal, right? V naught is V2 by Y. But how are we going to solve this? To solve this, a simple way is you can simply write V naught is A times of V1 minus V2. V naught is A times of V1 minus V2. Now, for simplicity, let me take an amplifier gain as 1. Gain A equal to 1. Just for our analysis, right? We'll make A as 1. And V1 is 3. And V2 is V naught by 2. So V naught is 1 into 3 minus V naught by 2. Right? So if you solve this, you get V naught equal to 2 volt and V2 equal to 1 volt and V1 is 3 volt. So let me, the final answer is something like this. This is 3, this is 2, this is 1, and the gain is of course 1. So what is 3 minus 1? 3 minus 1 is 2, 2 into 1 is 2. So these are the numbers. If you simply apply the equation, V naught is A times of V1 minus V2. But it's always debatable now. The reason is, just in the previous class, or even just now while doing the what you call the duty cycle problem, I said that the output is either at plus VSAT or minus VSAT. And now I'm suddenly saying that no, it has finally backtracked and it has found a point where the voltage is stable now and the output is at 2 volt and minus terminal is at 1 volt. And the difference is 2. 3 minus 1 is 2. So 2 into 1 is 2. So it will finally track down to this voltage, right? So as a student, it never entered into my head. Now, when you suddenly give negative feedback, you say that the op amp is not saturating. But if you don't give feedback, you say that it has saturated, right? So what I've done, I remember what I've done is um, like a child's play, right? If you want to explain it, negative feedback to a normal kid, right? So how would you explain it? So the first thing what a student can do is he can prepare a simple table like this. Right? Now, like in the previous case, I said the output can be either at plus VSAT or minus VSAT. So we can start off like this. What if the output is 8 volt? What if the output is 8? So it's 8 here. It's 8. Now you have to backtrack. You have to backtrack. After V0, what is V2? What is V2? This V2 is going to be 8 by 2. It's going to be 8 by 2. And V1 is 3. V1 is 3. So 3 minus 8 by 2, that is minus 1. What if you again backtrack, right? And say 3 minus of minus 1 by 2, that's minus 0.5. It is going to be 3.5. So that means the op-amp is getting restless. It's not stable. I am giving you a nice stable value here. I said output is 2. This is 3. This is 1. 3 minus 1 into 1 is 2. That's it. But now, by the same multiplication of V0 equal to A times of V1 minus V2, you can see that the numbers are changing. It's so restless. 8, 3 minus 8 by 2 is minus 1, and then 3.5. And then 3.5, if you subtract here, it's 3 minus 3.5 by 2. So 3 minus 3.5 by 2 with a calculator, you get 1.25. And then this 1.25, backtrack, 3 minus 1.25 by 2. Let's see if it is if it hits that point. 1.25 by 2. 1.25 by 2 is 0.625 is 2.375. Three minus 2.375 by 2. So it's almost coming to 2. 1.8125. And then it is 3 minus 0.90625. So this is almost like 1.9, it's almost 2. And then you backtrack here, it is 3 minus 2 by 2 is 1, which is 2. And then 3 minus 1 is 2. And then 3 minus 1 is 2. So here, beyond a point, we have found that it has become stable. But here, in these values, he's totally restless. Now the question is, how is op-amp knows that it has to come and stay at 2 volt? It doesn't know, right? It doesn't know. I mean, yesterday, I was playing hide and seek with my daughter, right? And I asked her how she's able to locate me. She gave a very, nice answer. She said that it's simple, Dad. I have to search you in every room. That's it, right? So I go, I find a room, you're not there. I'm restless. So I keep searching. And finally, when I catch, I'll stay with you. I'm stable there, right? So op-amp does the same thing. It does not know. See, when you study control systems and negative feedback, you always say that the value is predictable. It predicts that value, does not know that value, just predicts it, and finally hits that point. How does it hit exactly there? We don't know. But if it is any other point other than that, it is restless. That's the reason finally it will attain that stability. Are you getting? I mean, a simple analogy, if you, I mean, some of you who are, suppose your friend says that he's at a function hall, right? He's at a function hall, he's attending a function and you have to go and meet him, right? Suppose this is a road. Of course, these days we have Google and GPS, but I'm just telling you, some of, especially boys, boys are restless, we know it. So they generally go like this from, say, point A. Suppose the functional is somewhere here. So there's a point where you have to reach, right? So what do? They take a bike and restlessly they go till here and they meet a person A. Now this person, he's another boy. So he doesn't give you an exact location. He simply says that, no, it is somewhere there. You came a little far. Now this guy, okay, in the same direction, he'll go backwards and meet another guy, another boy here, B. Now this fellow will say that, no, you have to go that side only, so the functional is there. But this time, what do? He does not go till here because he already tried. This time, he'll go only till here and he'll find another guy C. And he'll say that, no, is this the functional here? He said, nah, you again crossed it. Now this fellow again, he scratches his head. But he'll not go till here. He finally go here and then finally, bingo, he'll zero it. So how does he arrive there, right? Because he searched everywhere, right? So he went up and down like the op-amp, you can. So what is the output? If you can track that voltage, we have calculated, we have predicted it that it has to be at 2. It has to be at 2. But did it arrive at 2 and become stable? No, because if it starts at 8, the next iteration it jumps to -1. And the next iteration that look, it keeps on going back and forth and back and forth and back and forth and back and forth like this. So it went from 8 to -1 and then it reached to 3.5. So this time it didn't go till there, 3.5. And then it came down to 1.25. And then 1.25, 2.375. There's 1.8 something, and then bingo, 2 volt. You reach there. So this is the major advantage of negative feedback is stability, and you can predict it. So the moment you design a circuit and say that op-amp you have to reach there, he will go come what may. He's going to reach there come what may, because if he's any other value other than that, he's restless because the pattern, the value keeps on changing. Because if he goes to 8, the VD will become negative. Boom, he goes down, the VD will become positive. Then he thinks that, no, he has to go up. And again, the VD becomes negative. When VD is negative, your output is negative. So he pushes down and back and forth and back and forth, and finally it's there. So next time, we are not going to do this analysis, but this analysis is just to tell you that he is not going to be anywhere else other than what voltage? The 2 volt, which you have predicted with a simple formula, V0 equal to A times of what? V1 minus V2. Just think about it for a while. And it's not just 8. You can start off with 12. If it is 12, what will happen? This becomes 6. The moment it becomes 6, 3 minus 6 is negative. He says, oh, that's not positive. You have to go in the negative direction. So the moment you go to the negative, you backtrack the next iteration, VD will become positive. It says, no, you have to go up. And then once it tries to go up, the VD gets negative, it pushes him down. So he's going back and forth and back and forth. But once he hits a point 2, the next iteration, the 2 becomes 1, and 3 minus 1 is 2, and the 2 becomes 1, 3 minus 1 is 2, the system. But please, how much time do you think the op-amp takes to go from here to the stable point? Hardly a microsecond. You will not even know. You just switch on. The slew rate of an op-amp is 100 volt per microsecond. This is the switching speed of an op-amp is 100 volt per microsecond. So when you switch on, it's going to boom, go there and finally stay there. You will not even know that, right? And please don't do this type of analysis for gain 10 or gain 100 or gain 1000. I'm telling you, it'll take iteration over iteration. You will become tired. But he's going to hit that point, right? We're not so fast as op-amp, right? Those are electronic devices. They do 10 power 9 operations in a second, so you can't even believe them. Okay, so what is your observation now? The observation is the op-amp is not saturating. He is trying to locate a point where he can rest, where he can be stable, right? The major advantage of negative feedback is he will find a stable point somewhere, right? Now, the second observation which you have to do is, what happens if I increase the gain? Because when I increase the gain, now you should start seeing not the output, you should see how op-amp takes that output and drives its own input, So you have to see the relationship between V1 and V2, V1 and V2 now, right? So for gain 1, we know the numbers. What happens when the gain is 10? But please, I'm not going to put that table again. We'll do by the simple way, right? 1K, 1K. But this time the gain is 10. Now tell me, what is the answer? V0 is A times of V1 minus V2. Of course, this is also a gate problem, a simple gate problem. So in the place of A, I'll put 10. This is 3. And we know what is V2. V2 is V0 by 2. Just solve it and tell me the answer. V0 is 10 times of 3 minus V0 by 2. What is V0? Good. So V0, this time, students are saying that this V0 should be 5. And this guy is 2.5 after backtracking. And he's 3. The gain is 10. Let me see whether after attaining this number, will he be stable? 5 becomes 2.5. 3 minus 2.5 is 0.5. 0.5 into 10 is 5. Then again backtrack. 5 becomes 2.5. 2.5. 3 minus 2.5 is 0.5. 0.5 into 10 is 5. And again you backtrack. So this is a stable point. Excellent, right? So these are the numbers now. Now, in the previous example, when the gain was only 1, this was 3, this is 2, this is at 1. Am I right? Now, what is the error voltage? What is the difference VD in the first case? The difference VD was 3 minus 1, that is 2 volt. 2 volt, right? 2 volt is the difference. Now, when the gain is 10, can you see that the error between the two terminals is slowly converging? The negative terminal is slowly trying to reach the positive terminal, right? This is the phenomena is something called virtual short. Slowly, yeah, I will show you that this voltage is not going to be 2.5, it's going to be 2.999999. So it's almost 3. So op-amp, by continuous backtracking, he is going to attain a value which is almost equal to 3. Now you might say, when he attains exactly 3, then what's the big deal in that? The big deal is, if I give an audio signal at plus terminal, and op-amp generates the same audio signal at minus terminal from the output, surprisingly, that output is 2 times of the input. It's an amplifier. So you want an output to amplify the 3 volt. You want the output to amplify 3 volt. The 3 should become 6. When 3 will become 6? Tell me, when 3 will become 6? If I can get the 3, same value If I want it to amplify in a linear fashion, the signal should be amplified 2 times, 3 times, 4 times, like that. If I want him to amplify 2 times, I have to bring back the 3 here, because if the inverting terminal is 3, then it becomes 6. How is this possible? This is possible when Stephen Black introduced negative feedback, right? Stephen Black is a man who introduced negative feedback. He said that the gain should be at least 40 dB more than your requirement, at least 100 times more than your requirement. So if you want a gain of 5, at least 100 to 500, right? So what if I make it 1000? I'll make it 1000 here. But the practical op amp is 10 power 6. I'm just making it 1000. So from now onwards, you don't have to worry. You will solve this problem still in a very, very simple fashion. Oh. Right? So now you tell me, what is V naught? V naught is 1000 times of V1 minus V2. It is 1000 times of 3 minus V naught by 2. I think now there is no need for you to do this. You can almost say that this V naught is 5.999, right? 5.999, which is almost almost 6 volt. Then your V2 is 6 by 2, which is almost 3 volt. And your V1 is almost 3. So if the gain is 40 dB more than your requirement, you can blindly say that if this is 3, this is almost 2.99999. And the difference is being amplified around 1000 times. It is almost 6 volt. What is 6 by 1000? 6 millivolt will be the difference. So please, I'm not doing the exact subtraction. It's not 2.999. It is 3 minus 6 milli, right? It's going to be 3 minus 6 millivolts. It's almost 3. There's almost 3 volt here, right? So I repeat, in negative feedback, you can predict the values, right? The predictability and stability. These are the 2 main criteria in negative feedback. So the op amp is not going to saturate, right? He's going to find a point between plus Vsat and minus Vsat. That is one observation. The second observation is the error between the 2 terminals will keep on converging, and the voltage at non-inverting will almost be equal to, please, it's not exactly equal. It's not possible, because if the plus terminal is 3 and minus terminal is also 3, then what is the difference? It is 0. When the difference is 0, then there won't be any output. Please, it's for all our calculations, that is not 3. That is not 3. It is going to be 2.9999. And the difference is such a small number. For all practical purposes, we are neglecting that difference. Are you getting, right? So predictability is one aspect. You can predict the values even before connecting all this. The second thing is stability, right? And the error between the 2 terminals will keep on converging. The voltage at non-inverting will almost appear as voltage at inverting if the gain is very high, right? If the gain is very high. So these are the, if you study a book called The Art of Electronics, right? The author, right? He mentions a statement. He says that in a fancy way, he says that golden rules to start op-amp problems. If you want to mention the golden rules to start op-amp problems, what is the golden rule? Golden rule, right? If A is large, The golden rule to start op-amp problems if A is large is the voltage at non-inverting terminal is equal to voltage at inverting terminal. The voltage at non-inverting is equal to voltage at inverting. It's not exactly equal. The difference is a very small number that is being actually amplified. Because the gain is very high, the difference is very, very small, is almost equal to the voltage at non-inverting is almost equal to voltage at inverting. The second golden rule, I told you, op-amp input resistance is very large, RID. Suppose this is 1 gigaohm, 1 gigaohm. This is the op-amp. And the difference is already a microvolt or a millivolt. Then what will be the current drawn by op-amp? Already the difference is very small. And the input resistance of amplifiers is also very large. Then what will be the value, the magnitude of that current? IOP is going to be microvolt divided by gigaohm. So this is 10 power minus 6 by 10 power 9. So op-amp is going to draw a tremendous current of what? 10 power minus 15 ampere. This is a signal current. It is a signal. Already the signal is, see how good an op-amp is. Last class I told you, a student was asking me a doubt. Sir, what if I have a 1 microvolt signal, a very, very dead signal? Can there be an amplifier which will amplify? Yes. Because he does not draw any current. Already the signal is dead. What current it will give? He is already designed in such a fashion that he's not going to draw any current, but he will amplify that small weak signal by the help of the power supply, right? By the help of the supply here. So please, should I consider this 10 power minus 15? For all practical purposes, I say that op-amp draws no current. Op-amp draws no current. So if I want to start op-amp problems, these are the two rules you have to remember, right? What is the first rule? The voltage at plus terminal is almost going to be at voltage at minus, or the inverting voltage will always be equal to the voltage at non-inverting, right? And op-amp is never going to draw any current. Come what may, the input resistance is very high because the first stage of an op-amp is a differential amplifier with a cascode connection. It's a huge input impedance. It's not at all going to draw any current, right? It's very, very, because the signal is in voltage form, right? Current is extremely small, right? So op-amp is not going to draw any current in the sense, the signal current is quite small. And the voltage at non-inverting almost appears, the voltage at inverting almost appears to be equal to voltage at non-inverting with a slight error, Yes. Now, this rule that the voltage at non-inverting is equal to voltage at inverting, in books, this is something called the concept of virtual short, right? It is something called the concept of what? Virtual short. So you can see the numbers here. When the gain is only 1, the error was 2 volts. VD is 2 volts. Now the VD is only 0.5 volt. It has decreased. Now VD is a 6 millivolt. When the gain is 1000, VD is 6 millivolt. When the gain is 10 lakhs, it's going to be 6 microvolt. The gain is 10 lakhs. It's going to be 6 microvolt, right? So the difference between the plus and minus is going to be hardly a microvolt, right? So for all practical purposes, we say that both the voltages are same. The voltage at non-inverting is equal to voltage at inverting, and op-amp draws no current. And hereafter, don't do all this table, right? Don't waste your time doing that, because whether you like it or not, it is going to hit that point, right? And that you can very easily get by this, wonderful equation. V naught is A times of V1 minus V2, right? Or if you want, I can mathematically prove it, because we all know nature obeys mathematics, right? If somebody can validate a statement with mathematics, then there is no issue. We will have to believe it. So let me prove this with simple mathematics, which is there in any book, controls book. So the A in control systems is G, right? G. This is V1, this is V2 and VD. V naught is A times of VD or G times of VD. Now this V naught through a voltage divider is given to H. Now in this case, H is 0.5, because if output is if output is 6, this is going to be 3. If output is 5, it's going to be 2.5. So this is the op amp, right? So let us prove virtual ground mathematically. What is the relationship between V naught and V2? Or let me repeat this. What is the relationship between VD, V1 and V2? VD is V1 minus V2. And what is the relation between V naught and VD? V naught is G times of VD. This is a forward path, and this is the feedback path, feedback. In feedback path, who is the input? V naught is the input, and V2 is the output. So V2 is H times of V naught. So now you tell me, what is, what is V2? V2 is H times of V naught. And what is V naught? What is V naught? I mean, you know the negative feedback equation, right? It is G by 1 plus GH times of V1. G by 1 plus GH times of V1. So what is V2? V2 is going to be V1 by 1 plus 1 by GH. 1 plus 1 by GH, right? Now, when the gain was 1, when G is 1 and H is 0.5, first case, what did we get? Case 1, G was 1, H is 0.5, and the input V1 is 3 volt, right? Then we got V2 as 1 volt. V2 as 1 volt, right? In the first case, 1 by 1 into 1 by 0.5 is 2. 2 plus 1 is 3. 3 by 3 is 1. Yeah. In the second case, what did we do? We took the gain as 10. And of course, H is 0.5. V1 is 3. And this case, V2 was 2.5, I remember, because the gain is 10, 2.5. And case 3, what if the G is 1000 or say 10 power 6 and H is 0.5? If V1 is 3, you can almost say V2 is almost equal to what? 3 volt, right? So now tell me, if GH is large, or G equal to infinite. If G equal to infinite, then your V2 is equal to V1. This is called the virtual short. The voltage at non-inverting is equal to voltage at inverting, right? And what is VD? What is VD here? VD is going to be V1 by 1 plus GH. So if GH is large, the error VD is almost 0. The error VD is almost 0. So this is, any controls book will tell you, if you take an op amp and connect some resistors and feedback, then the relationship between V2 and V1 is V2 is V1 by 1 plus 1 by GH. So V2 is almost equal to V1. See, this is the main reason why of all the topics in analog, op-amp problems are quite simple. The reason is because of these two simple assumptions. One is whatever voltage you give, the same voltage is manifested at the other terminal, and there's no current that it is going to draw. So if you connect some resistors, so it's a problem of only resistors, right? It's a problem of only resistors. What if you connect 9K, 1K here, 9K and 1K? This is 9K and 1K. And you give 1 volt. Op-amp has to bring 1 here. Op-amp has to bring 1 here. If it is 1, this has to be 10. If it is 1, because of the voltage division rule. One volt equal to V naught into 1K by 9K plus 1K. So your V naught is going to be 10. So that means what? If I give a small triangular waveform here, triangular waveform, how op-amp knows that it has to amplify exactly the same triangle? He does not know. But he will send some current from the supply. He keeps on modulating the current from the supply and keep varying V0, V2, V0, V2, V0, V2. The currents keep on changing in a fashion where the inverting terminal gets exactly the same triangular waveform. But when this is triangle, this is already 10 times of that waveform. So if he doesn't get this, he keeps on changing until the same voltage is manifested here. So if you want to amplify a triangular waveform, you just give to the non-inverting terminal and the current from the supply is being modulated. So what is an amplifier? Basically an amplifier, by definition, what is an amplifier, right? An amplifier modulates the current from the supply to get an amplified version of a small controlling input. So what basically an amplifier does is it keeps on sending the current from the supply. The moment the device is on, the transistor is on, the MOSFET is on, the op-amp is on, the currents keep on flowing in such a fashion that the voltage at non-inverting exactly is voltage at inverting, but the inverting is not coming from non-inverting. You know it. The inverting is not coming from non-inverting. The invert is coming from the output, and output is coming from the supply. So the supply current is keeping on modulating in such a fashion that you get exactly 10 times of that waveform at the output. Are you getting? Just think about it. See, when I first learned an op-amp, thinking that, because see, whenever we find a voltage divider, what do we think? Suppose I'm having a voltage divider. The first time when you look at the voltage divider, what do you think? You are giving 5 volt here. This is 9K, 1K, or you're giving 10 volt here. This is 9K, 1K. You're getting 1 volt here, 1 volt here. Now, when you look at the voltage divider, just tell me who controls whom? Who is the controlling factor? Who is controlling whom? We think that 10 volts is the voltage that you're giving, source, because of which we got 1 volt, right? So the 1 volt is only an outcome of the 10 volt. Now, what I'm saying is, suppose this, instead of 1 volt, I have 2 volt here. If I have 2, then automatically this has to be what? 20. So what I'm trying to say is, can this 1 volt control the 10 volt? It's a voltage controlled voltage source. Voltage controlled voltage. So I want the drop here. I will decide the drop. And that drop is going to decide the source at the output. So it's fascinating, right? So it's a simple voltage divider. We know it's an attenuator. How an attenuator will decide an amplifier. How an attenuator is going to decide an amplifier. So instead of this 1 volt, so what we have to do is the same voltage divider, you give it to an op amp and see the fun now. The same voltage divider, you give it to an op amp, and now you can see the fun. This is an attenuator, we know it. From an attenuator, if this is 1 volt, if this is 1 volt, 1 volt up and down, this is going to be 10 volt up and down. We know it. But we thought that this is the input, this is the input, and this is the output. But what I'm saying is the same divider, if you give it to an op amp, and if you give the triangular input here, what happens? Op amp from the supply is going to generate the same triangle, but when this is a triangle, this is already an amplified version of the input. So it is a voltage controlled voltage source. It's a voltage controlled voltage source, right? So the input is in voltage form, the output is also in voltage. So you get an amplified version with a divider, right? So you know that it is attenuating by 1K by 9K plus 1K, but it's attenuating by 1 by 10. That means the output is an amplified version of 10 times, amplifying 10 times, right? So please think about it. So when I first learned an op amp, I felt like, wow, this stuff is really cool, right? So you build an attenuator, and you know how much it has to attenuate from the output to that terminal, and then give an input and see the fun. When you see the fun, the signal what you apply is going to be across the attenuator, but the output is going to be the amplified version. Are you getting? Think about it, right? If you don't want to think, no problem. Just remember these two at least, right? Because for solving anything, these two are enough. Voltage at non-inverting is equal to voltage at inverting, and op amp draws no current. Op amp draws no current, right? Okay, so now let's get back to the first amplifier. What is the first amplifier in books? What's the first amplifier in books? It's the non-inverting amplifier. This is a VCVS. You're going to get V naught equal to K times of V or K times of Vs. You can connect the load if you want here, load RL. Okay. So what are the golden rules to start op amp? One is V1 equal to V2. This is V1. This is V2. V1 equal to V2 equal to Vs. What is V1 with respect to ground? That is Vs. This is something called virtual short. Virtual short, right? Now, What is the second condition? The second condition is op-amp draws no current. This IOP is 0 at both the terminals. Op-amp is not going to draw any current. So you can take some current here, I1, this I2. So now you can apply KCL. So the currents that enter the node here is equal to the currents that are leaving the node. So I1 is equal to IOP plus I2. Now tell me, what is IOP? IOP is 0. What is the reason? This is a gate bit. Why op-amp draws no current? Because op-amp has high input resistance. Right? So please see carefully. This is the first amplifier. Now we are starting op-amps, right? Enough of all the fun that we have done. Now we'll get back to serious business, right? So we, throughout the day today, till the end of the session, we are going to apply only these two rules, the golden rules. V1 is equal to V2 and op-amp draws no current, right? So then your I1 is going to be I2. I1 is going to be I2. What is I1? What is I1? This is I1. And what is I2? Because the page is very small, so the same diagram, I'm drawing it here again, right? I1 is the current flowing through R1 and I2 is the current flowing through R2. Now you can give me Ohm's law. I1 equal to I2. I1 equal to I2. So what is Ohm's law here? I is equal to V1 minus V2 by R, right? It is 0 minus V2 by R1. This is V2 minus V0 by R2. So from here, you get V0 equal to 1 plus R2 by R1 times of V2. But we all know that V2 is same as V1 and V1 is nothing but our Vs. So V0 is going to be 1 plus R2 by R1 times of Vs, or it is of the form V0 equal to K times of Vs. So whenever you get a relationship V0 equal to KVS, it's a voltage amplifier. I0 equal to KIS, it's a current amplifier. I0 equal to GMVS, transconductance. V0 equal to RMIS, trans resistance. So V0 equal to KVS. And most important is, whenever you are designing an amplifier, the output V0 should be independent of RL. The output V0 should be independent. It should not be a load controlled voltage source. No, voltage controlled voltage source. The output voltage is controlled by input voltage, right? So V0 is 1 plus R2 by R1 times of Vs, right? So best thing is you have to remember the formula, right? Or if you want, you can apply KCL. So simple, right? V0 is 1 plus R2 by R1 times of Vs. Some books call R2 as RF, like the feedback resistor, 1 plus RF by R1 times of Vs. So an amplifier modulates the current from the supply to get an amplified version of the small controlling input. The controlling input is very, very small. The controlled output is much larger. But please, energy is neither created nor destroyed. So don't think the small signal will enter in and suddenly become large. This is not a transformer, okay? In a transformer, you keep stepping up and stepping down, right? So the voltage, the small voltage becomes large, but the current driving capability will reduce. No. Amplifiers are not transformers. There is no transformation in electronics. There is no transformation in electronics. There is only conversion. No, never call an amplifier as a transformer. Call him as a converter. V to V, V to I to V, I to I. An amplifier is a converter, right? It's not a transformer. So it needs an additional power supply to modulate that current. So the op-amp modulates that current from the supply to get an amplified version of a small controlling input. Yeah, I forgot the voltage divider. We can solve this by a voltage divider. See here, the Vs, voltage at non-inverting is Vs. It is appearing at the voltage at inverting. So what is V2? V2 is nothing but the voltage at inverting terminal with respect to ground. So method 2, if you don't like KCL, then you can do by voltage divider rule. So what is a voltage divider rule here? We had R2, and this was the output. And then we had R1, op-amp draws no current. And the voltage across R1 happens to be Vs. Vs. So it is the Vs, the voltage at R1 is coming from the output by backtracking, right, from the supply. So in my first class, I told you a voltage divider will always give you a fraction of the input voltage. So what is Vs? Vs is going to be V0 into R1 by R2 plus R1. R2 plus R1. So from here, V0 is 1 plus R2 by R1 times of Vs. So this is the formula. This is the formula, right? So this is not by KCL, this is by the voltage divider rule, right? Well, how do you get the voltage divider? A student was asking me, if you take some current I, what is Vs? Vs equal to I into R1. I into R1 by Ohm's law, right? Ohm's law says that the voltage is equal to the current into the resistance. But what is the current in the loop? The current in the loop is V0 by R2 plus R1 into R1. So this is called the voltage divider rule, right? Or you can solve it by Ohm's law, right? Method 2. Some students like method 2. They don't want to apply KCL. They say that we know that the voltage at inverting always comes from the output. It is a voltage controlled voltage source. This is a voltage source. The amplifier is a voltage source. It's a voltage source. So that source he's trying to backtrack in order to build the same signal with an error equal to 0. So the error becomes 0 only when the gain is large, right? So you can use the voltage division rule formula, right? Or you can use KCL. KCL. What if you want to apply KVL? KVL is, I told you, what is KVL? The algebraic sum of voltages in a loop is always equal to 0. So you can solve it by KVL also, right? Okay, you want to do by KVL method 3. What is the best method? The best method is remember the formula, right? A simple formula, 1 plus R2 by R1 times the Vs, right? So you don't have to do anything, right? Because this is a basic amplifier, the first amplifier in any book, right? Method 3, if you want KVL, KVL needs a loop. You have to form loops now, right? KVL. So we know that V1 is almost equal to V2. That means VD, which is V1 minus V2 is what? 0. Am I right? So KVL. How do we apply KVL here? KVL deals with the drop. This is V0. You can take some current here. And what is the current drawn by an op-amp? 0. So this current and this current both are same. This is R1, R2, and yeah. And what is the drop VD here? 0. I1 or I1 here. Right? Current always flows from a higher potential to lower potential. This, when you're applying KVL, you need all the polarities now, right? So tell me, what loop shall we take now? What loop shall we take? Can I go a loop like this? Or what is that video game where I remember, there's something going like this, tuck, 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 and eating. It goes everywhere, right? It's some video game. If you remember that. So like that, I want to go all the way from here back down here, right? So I have two loops now. So tell me, I will go from Vs and then come back to the same point. Minus to plus, minus Vs plus 0 minus I1 R1 equal to 0. So I1 equal to, what is I1? Minus Vs by R1, right? And this loop, minus Vs plus 0 plus I1 R2 plus V0 equal to 0. So V0 is going to be Vs minus I1 R2. So it is Vs. What is minus I1? It is Vs by R1 into R2. So from here, your V0 is going to be 1 plus R2 by R1 times the Vs. Please, next time I will not do by all these methods, right? Anything that we find it easy, we will do it. Because students keep asking, sir, should we always apply only KCL? Should we apply whatever you feel like applying, you apply. It's a network. But the KVL, you always have to have loops, like it's a big headache, right? Go round and round. You have to climb the op amp, go all the way, right? Fine. So you get the same answer. So one loop is here and the other loop here is still V0 is 1 plus R2 by R1 times Vs. So anything you wish, you can do it. My favorite is this. I'm a lazy fellow, right? The voltage divider. This is also okay. This is a favorite when I was in college, right? Slowly keep on applying KCL and do it. Okay. Or do you want to do by the method which I told you? Suppose you don't know virtual ground, and we don't know those rules, because those rules are shortcut. If you have forgotten that rules, what is the basic idea from where the whole story started? It is V naught is A times of V1 minus. Please never forget that. An op amp is a high gain difference amplifier. So V naught method, this was actually our first method, in fact, right? Method 4, right? But we don't have to do by this method because the number of steps are more. We have seen V naught is A times of V1 minus V2. So this is where we have started actually, right? This is where we have started. And V naught is A times of V1 minus V2. So am I right? So it is A times of V1 was Vs, and V2, what is V2? What is V2? What is V2 here? V2 is the by voltage division. You want me to draw it again? V naught into R1 by R2 plus R1. Yeah, let me draw it here again. The same non-inverting amplifier, I can draw it like this. This is Vs. This was R2, R1. This is V2. This is V naught, right? Here you have a load. The output does not depend on the load here, RL. Yeah, this is V naught. Yeah, V naught into R1 by R2 plus R1 is V naught. So from here, if you solve, your V naught is A by 1 plus G by 1 plus GH, A by 1 plus A into R1 by RF plus R1, R2 plus R1. Yeah. Now you can divide numerator and denominator by A. It is 1 by A plus R1 by R2 plus R1. All of you, I told you, A is not 1, A is not 10, A is not 15. An ideal amplifier has A infinite. An ideal amplifier has A infinite. So when I put 1 by infinite, that's 0. So from here, your V naught is going to be 1 plus R2 by R1 times the Vs. So this is where we actually started, right? And then how did we start? We kept substituting A. A was 1, second problem A was 10, third problem A was 1000, and now A is infinite. A is infinite because we are doing an ideal op amp, right? An ideal op amp, virtual ground, sets up virtual ground. Not, please never apply virtual ground for gain 1, gain 10, don't apply, please don't apply, right? Apply only for an amplifier whose gain is very high. So V naught is 1 plus R2 by R1 times of Vs. All right. Okay, so I think you might not like this, isn't that method 4? But however, we snapped off only from method 4, and finally we made things easy. We said if A is very high, just go and see that V1 and V2 both are same. Vs, the same Vs is manifested here. So I've given you 4 methods. Please, hereafter I'm not going to do by all the methods. Only one method, something which we find easy, directly solve the answer. And I repeat, never, 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 never forget the golden rule. The golden rule. Where is the golden? Yeah. To solve any problems of op amp, when the gain is very large, voltage at non-inverting is almost equal to voltage at inverting, and op amp draws no current. Op amp draws no current. And what is the best thing? Just remember the formula. V naught is 1 plus R2 by R1 times of Vs. Am I right? The second amplifier, a very, very popular second amplifier, is the inverting amplifier. Inverting amplifier or trans resistance amplifier or current control voltage source, or your V naught is Rm times of Is. So input is in current form and the output is in voltage form, right? So this is the inverting amplifier. Oh my God. Where's an eraser for this? Okay. So this is a trans resistance amplifier. Input is in current form and output is in voltage form. Now the doubt which generally a student gets it, when you give a signal to the plus terminal, you're calling it voltage. The moment you shifted it to minus terminal, now you're saying that the signal is not in voltage form, it is in what form? Current form, right? So I will explain this. But before that, can we get this relationship V naught equal to Rm times of Is, V naught equal to Rm times of Is, right? So let's start again. Voltage at non-inverting terminal is equal to voltage at inverting terminal, V1 equal to V2. Now let's see what is V1 and what is V2. V1, this is V2. V1 is nothing but 0 volts, right? V1 equal to V2 equal to 0. And now, what is the current drawn by an op amp here? 0. So entering current is equal to leaving current. Suppose this is Ix, right? So now you can give me KCL. KCL is Is equal to 0 plus Ix, which is Ix. But what is this Ix? Here we have V2, which is 0. This RF, V naught, and here you have Ix. What is Ix? By Ohm's law, it is 0 minus V naught by RF. So your V naught is minus RF times of Is. Your V naught is minus RF times of Is. So what is the trans resistance? Trans resistance is denoted by Rm. Rm is output voltage by input current. So the trans resistance is minus Rm because this is of what form? This is of the form V naught equal to Rm times of Is. So in the place of Rm, what do we have? We have minus Rf. We have minus Rf. So this is the trans resistance of the amplifier. Now the question is, why the input is in current? It should be voltage, right? It could have been voltage. Why is it in current, not voltage, right? Now, I can program this current. Programming the current Is with Vs and R1. I can program the current IS with Vs and R1. So this is the popular inverting amplifier in book. Because if I directly draw this amplifier, what is the problem? The student will think that this amplifier and the first amplifier both are same, except that there is 180 degrees phase shift. No, there's a completely different topology. The signal at the input is not in voltage. It is in what form? Current. I will show how it is. But before that, let us solve this, and then we will logically have an explanation for it, right? So we're going to have a logical explanation to the reason that why plus terminal is for voltage, why minus terminal is for current, right? So before that, the voltage at non-inverting is 0, so the voltage at inverting is also 0. And the current here, if it is I, op-amp draws no current, so this current should also be I. So tell me, I is I. Of course, I is I, right? What is I here? I is Vs minus 0 by R1. What is the same I traveling here? Because this current is 0. 0 minus V0 by Rf. So this is also very, very popular. Most of the students know this. It is minus of R2 by R1 or Rf by R1 into Vs. Very, very important. Right? So what are the two formulas which I want you to remember? Non-inverting amplifier 1 plus R2 by R1 or 1 plus Rf by R1 times the Vs. Inverting amplifier minus Rf by R1 times the Vs. Right? Now, can we have a logical explanation that why the input is not in voltage, it is in current for the inverting terminal. For the non-inverting, it is voltage. Oh, some students are saying, the game where when you are playing KVL, remember the video game. It's called Pac-Man, right? Some student said it's Pac-Man game. Nice. Okay, so I repeat, the non-inverting amplifier is 1 plus R2 by R1 or 1 plus Rf by R1. Inverting amplifier, it's minus Rf by R1. So let's have a simple logical explanation for this, right? Now, suppose I have two components with me. One is a 1 volt source and the other one is a 1 ohm resistor. I have 1 volt source and a 1 ohm resistor, right? Now, can you give me two extreme conditions, right? A short circuited condition and an open circuited condition, a high impedance condition and a low impedance condition. How will you connect this 1 volt with a 1 ohm to have an open circuited condition and to have a short circuit? Let's have two extremes, right? Open circuit, short circuit. For open circuit, you would probably connect it like this. This 1 volt with 1 ohm. 1 ohm. Now tell me, in an open circuit, what will happen to V? V is going to be maximum 1 volt, and the current I is going to become 0, right? Current I is going to become 0, V is 1 volt, right? Now what happens if I try to short circuit this? There's a maximum current that you can expect from this, because you're literally short circuiting here I, and what is the voltage across the short circuit? Yeah, two extremes, right? The current I is going to be 1 volt by 1 ohm, which is 1 ampere, but the voltage across the short circuit is 0. So in a short circuited condition, the moment you connect a microphone to an inverting terminal and you say hello, the moment you say hello, the amplifier is going to take the juice out of him, is going to put a virtual short and literally draw a current V by R at the inverting terminal. I'll show you. But if you give it to non-inverting, he's not going to draw any current. There's an op amp here. I give 1 ohm with 1 volt, 1 ohm with 1 volt to the non-inverting. To the non-inverting. I give the same 1 volt with 1 ohm to the inverting. To the inverting. What is the op amp behavior in these two cases? Forget about all the other resistors. We're just talking about 1 volt with 1 ohm. If you connect 1 volt with 1 ohm, the current drawn by an op amp is 0, and the whole 1 volt is being manifested here. So it's 1 volt with a current 0. It's exactly an open circuit, a high impedance condition. So somebody who sees from here, right? Who literally sees from here, right? Sees from here at the input side. Okay, just for fun, right? So somebody who sees from here, he thinks that this guy is a perfect open circuit. But somebody who sees from here, he thinks that the transducer thinks that this guy has literally short circuited my transducer. So a transducer can, so you might draw a Thevenin equivalent here, but that's nonsense, because this is not a Thevenin. This is not because you're literally drawing the whole current here. When you draw a Thevenin equivalent, there should be an open circuit, right? There should be an open circuit. When you draw a Norton equivalent, it's a short circuited current. You're literally short circuiting, you're taking the juice out of him, completely drawing a current of 1 ampere. See, there's a current of 1 ampere, and the voltage that is sensed here is 0 volt. The voltage that is sensed here is 0 volt. The current here is 1 minus 0 by 1. 1 minus 0 by 1 is the current I. So you might think that you have given a Vs with R1, but op amp thinks that I'm sensing 0, forget it. But I'm sensing also a current equal to Vs by R1, which I'm sending it to the feedback for processing, for analog processing. I'm using the current, not the voltage. Because you might have given Vs, but I'm sensing only 0. So what is this condition where it senses 0? This has to be a short circuit condition, a low impedance condition, right? So inverting terminal is always, when a transducer is connected to the inverting, you connect a microphone to the inverting and you say, hello, hello, your voice is converted in current form. The same microphone, you give it to a non-inverting and you say, hello, hello, your voice is converted in voltage form. Because op amp draws no current. Energy is neither created nor destroyed. If he's not drawing in current form, it will be in voltage. If he says that my voltage is 0, definitely the signal will be in current. The signal can have a voltage form or a current form, right? So if the voltage is 0, it has to be in current. The current is 0, it has to be voltage, right? Think about it. But formally, we will take up this topic in feedback amplifier. So I'll show you that this is shunt feedback, and not now. The shunt feedback. Shunt, I told you, low, high-low voltage amplifier, low-high current amplifier, high trans conductance, low trans resistance. This was the summary of amplifiers. High-low series shunt voltage amplifier, shunt series current amplifier, series trans conductance, shunt trans resistance. This is a shunt amplifier. The topology is shunt. Definitely the signal will be in current form, and at the input, and the output will be in voltage. But how it is, Shanshan, you have to wait till I take up feedback amp, because complete analog subject is by alleviating the problem one by one. Whenever you take up a new topic, you will hardly learn just one or two things, that's all. And you will keep on proceeding. And then you include one extra, keep on proceeding, and you include it. If you include everything in an amplifier, then it just blow your mind. Are you getting? So for today, and maybe even for tomorrow, it's like voltage at non-inverting is voltage at inverting, voltage at non-inverting, voltage. With this, we are going to build adder, subtractor, differentiator, integrators, everything, right? So the plus terminal is for voltage and the minus terminal is for what? Current, remember, right? It's not voltage. It's going to send only a zero voltage there, but the signal is in current form. So I make no mistake when I say that I am programming a current IS here, IS here, IS here. I'm programming a current IS, the source current IS, with VS and R1. I'm programming a current IS with VS and R1. The signal here is not in voltage form, it's in current form, right? Okay, so now we will start solving simple problems, simple problems. Find V naught, op amp, ideal. Find V naught, op amp, ideal. Find V naught. in all the problems, the op amp is ideal. If it's not mentioned, you have to take it as ideal. Okay, so let's start solving. So what are the two realistic assumptions? The two realistic assumptions, it's not an assumption. When I say assumption, don't think it's an assumption. It's a very, very realistic assumption. It's true that this potential is going to be this. So if this is 2 volt, this voltage is also going to be 2. Voltage at non-inverting is voltage at inverting. What is the current drawn here? 0 ampere. Now, entering current is equal to leaving, right? If this is I, it's also I. So I is equal to I. Tell me, what is I? 0 minus 2 by 1K is 2 minus V naught by 2K. So your V naught is going to be 1 plus R2 by R1 times of T. volt, right? So how much is this? 2 plus 1 is 3. 3 into 2 is 6 volts, right? 3 into 2 is 6 volt. Right? Now, the current drawn by an op amp is 0. Op amp draws no current, 0 amps, 0 amps, right? So when the current here is 0, the whole voltage is going to be 3. This is 3. This node is also 3, right? So this 1K, in series with 1K, you have a huge input resistance here. Op amp draws no current, right? So the same 3 volt is manifested here. Voltage V plus, V1, V plus is equal to V minus, or voltage at non-inverting is voltage at inverting is 3 volt, right? Now, what is KCL? KCL says that the current entering can be the current leaving. So you can also take like this. Entering current is equal to leaving current. So what if this is entering and these two are leaving? So now you tell me entering is leaving. However you write, your answer is not going to change, right? Entering current is V0 minus 3 by 2K. And what is leaving here? Leaving is 3 minus 0 by 1K plus the current through the op amp is 0. From here, V0 is again 1 plus 2K by 1K times of 3. This is KCL, right? Current entering is equal to the current leaving. This is entering current. V0 here, 3 here, right? V0 is 3. In between, there's a resistor here, right? Okay, so this current entering is equal to leaving. So 3 plus, or 2 plus 1 is 3. 3 3s are 9. Oh, almost same. What was the previous one? 6, because of 2 volt. Okay. Or you can take a current here, entering is leaving like the previous problem. You can do entering equal to leaving. However you do, or sum of currents that leave a junction is 0. Sum of the current that enter a junction is 0. However you write, the law will take care. So your answer is not going to change, right? Yeah. Now, we have a voltage divider here again. Three volt, 1K, 2K, and here we have V1. V1 is equal to V2. V1 and V2 both are same. So what is V1, right? It is, you can directly apply voltage division, or V1 equal to I into 2K. What is I? 3 by 1K plus 2K into 2K. It is 2 volts. So naturally, because 1K, 2K we have connected. So what is the fraction? The voltage divider will always give you a fraction of the voltage. So across 1K, you have 1 volt. Across 2K, you're going to have 2 volt, right? The current remains same in that loop. So now V1 is equal to V2 equal to 2 volt. Right? Okay. Now, you can apply KCL. Entering current is equal to leaving current. What is the current drawn by an op amp? 0. So KCL V0 minus V2. V2 is 2 by 2K is entering. Leaving is V2 minus ground. Ground is 0 by 1K plus the current drawn by an op amp is 0. So from here, your V0, V2 is nothing but what is V2? 2. 2 volts, 2 minus 1. So your V0 is going to be 1 plus 2K by 1K times of 2. So it's 2 plus 1. 3 2s are 6. right? Entering current is equal to leaving current, right? Good. Most of you are giving answers slowly, right? Very good. Yeah. So this is the directly the inverting amplifier. So what is the gain of the inverting amplifier? See the voltage at the non-inverting V1 or V plus equal to V minus equal to 0 volts. So this is 0. So this node is also 0, right? So you can take entering equal to leaving or entering equal to leaving, your wish, right? So what is the current drawn by an op-amp? 0. So you can apply KCL and tell me this current entering is 2 minus 0 by 1K is entering. What are two leaving currents? 0 plus 0 minus V naught by 3K. So your V naught is going to be minus 3K by 1K times of 2. It is minus 6 volt. Am I getting 666 everywhere? Yeah, mostly 6. Yeah. Now, in the previous example, when the voltage divider, can you see that there was a voltage divider here and the voltage was getting divided, but the same voltage divider kind of a network we have seen here. But can you see that this 2K is actually a dummy resistor, right? If you want, you can apply KCL. But by looking at this circuit, you can just remove that 2K from the network. Why? The reason is the voltage at non-inverting is 0, so the voltage at inverting is also 0. I mean, something like bootstrap, right? So last class I told you, if you have a resistor and one end you have some voltage and the other end also you have some voltage, the same voltage, then what is the current flowing through this 2K? The current flowing through this 2K is almost equal to what? 0, right? It's almost 0. So you can just remove it and say that V naught is minus 3K by 1K into 2, right? You can do that. Okay, if you don't want, we will go by the normal method. So what is the normal method? The current entering is equal to the current leaving. So I have 3 leaving currents and 1 entering, right? So one current is entering the node and there are 3 leaving currents, right? Out of which op-amp draws no current, 0 amps. So give me a KCL there, KCL, right? It's 2 minus 0 by 1K is entering. And what are the 3 currents leaving? This current is, the current through 2K is 0 minus 0 by 2K. Op-amp draws a current of 0 plus 0 minus V naught by 3K. So your V naught is going to be minus 3K by 1K times of 2. Oh my God, this is again minus 6 volts. Oh, what am I doing? Huh? Anyways, yeah. So minus 3K by 1K into 2. But what happened to the 2K? There is no current, signal current that is flowing because op-amp converges the error difference between the two, right? So this is ground. The other end of the resistor is also at virtually ground. So there is no signal current that is flowing, right? Yeah. Now, all of you, if you want, you can, in your mind, you can even apply superposition theorem. What does superposition theorem tell you? What does superposition theorem tell you? It tells you that you have to take one source at a time, short circuiting all other voltage sources, right? And try to find the response, right? Individual response. Now, if I take 1 volt alone, what should I do to 2K and 3K? 2 volt and 3 volt. The 2 volt and 3 volt, I'll be grounding them. And because of a virtual short here, and the 2 volt is ground and the 3 volt is ground here, 2 volt is ground and the 3 volt is ground. Can you see the small star from my pen on the screen? Can you see? Yeah, I can see. Is it visible for you also? This is the first time I'm saying. I can move my pen and show you the location, right? Can you see this? Right? Yeah, this 2 volt and this 3 volt, if you can ground them, right? Ground them, then these two resistors have become dummy. You can simply say V0 is minus 1K by 1K into 1. Plus, you can take 2 volt alone, 2 volt alone, short circuiting these two. And you can say minus 1K by 1K into 2. Plus, minus 1K by 1K into 3. That's the answer, right? By looking at the problem, you can directly say that at any given time, there's only one resistor that is in usage. The other two resistors, they are not in usage when you are applying what theorem? Superposition. So like that also you can do, right? Okay, if you don't like superposition, KCL is always handy. I have 3 currents here, I1, I2, I3, entry. The current drawn by an op-amp is 0, and you can have I4 here, right? So what is KCL? What is KCL? KCL tells you that I1 plus I2 plus I3 equal to 0 plus I4. I1 plus I2 plus I3 is 0 plus I4. What is I1? 1 minus 0 by 1K plus 2 minus 0 by 1K plus 3 minus 0 by 1K is 0 minus V0 by 1K. So your V0 is going to be minus of 1 plus 2 plus 3. What is this? 1 plus 2 plus 3, 3, 4, 5. Oh my God, again 6. Huh? Okay, 6 volts. Now, can we name them? Because we just keep doing, one is a non-inverting amplifier, the other one is the inverting amplifier. Can you suggest some name for this circuit? I've given 1 volt, 2 volt, and 3 volt as the input, and I'm getting 6 volt at the output. So any name that you can suggest here, right? 1, 2, 3, 1 plus 2 plus 3, addition is 6. So we are going to call this circuit is an inverting adder or summer. Can we call like that? Right? Can we call this circuit is an inverting adder or a summer? The reason I'm calling it inverting is because of the negative sign here, the negative sign, right? Yeah, thank you. Yes, the star on the screen is visible, right? Okay, so these are simple, very, very simple problems. So we will carry on more problems. Can we take a break now? When we come back, we will have more problems to share, right? And then at the end, we can have some questionnaire like yesterday. You can ask the doubts. So many people have answered. I'm not able to see them. Wait, how to see this? Yeah. Oh, very good, very good, very good. So many people. Pac-Man, very good. 6 volt, 6 volt, 6 volt, 6 volt, 6 volt. Very good, very good, very good, very good, very good. Adder, summer. Excellent, excellent, excellent. I appreciate it, right? So we'll take a break. When we come back, we will have more problems to solve. Thank you. ஏன் வெளியில போறேன் டக்குனு காமெண்ட் ஒரே ஒரு வாட்டி வந்து சும்மா எனக்கு 7 பேர் தெரியும். Okay, so can you hear me? Can you see me? Can you hear me? Can you see me? Can you hear me? Yes.
Yes, sir.
Okay, so we'll continue. Fine, we not. Okay, have you solved it? Yeah. Let me change the color of the pen. Now, you can see that this node and this node, this node and this node, both are at 3 volt. So if you're fine with that, fine. Otherwise, you can draw the circuit like this. So there is 3 volt here. And here we have another 3 volt. So this is some problem we have already done, right? Okay. Now we all know that op-amp draws no current. At this terminal, the current is 0. At this terminal also, the current is 0. So what is the voltage at this point? This point, the voltage is going to be 3 volt. So the voltage at non-inverting is equal to voltage at inverting. Now, the current entering here is equal to the current leaving. So tell me KCL. It is 3 minus 3 by 1K equal to the current drawn by op-amp is 0 plus 3 minus V0 by 2K. So what is V0? This is 0 equal to 3 minus V0 by 2K. So what is V0? V0 is going to be how much? 3 volt. V0 is going to be 3 volt. So it's simple. If this is 3, this node is already at 3 and no current flows. So the 1K resistor, no current flows. So there's no drop through 2K also. When there's no drop through 2K, the same 3 volts is manifested at the output. Very good. 3 volt, 3 volt, 3 volt. Very good. Yeah. What about this problem? What about this problem? So the same thing, the same 2 volt is the same node here. This is 3K, 1K, 2 volt. And you have another 2 volt with respect to ground. Excuse me. Now, what is voltage V1? The V1 is same as V2. V1 is equal to V2. All right. What is V1 by voltage division? In the previous case, we have seen if two resistors of same value are there, then V1 is going to be 1 volt. It is same as V2. V1 is going to be 1 volt, it's same as V2. So now you can apply KCL. So tell me what is KCL? 2 minus V2 by 1K equal to 0 plus V2 minus V0 by 3K. V2 minus V0 by 3K. But what is V2? V2 is nothing but 1 volt. So 2 minus 1 by 1K is 1 minus V0 by 3K. From here, you can find V0. So it's 1 by 1K is 1 milli. This is 3 volt. I think it's 4, right? So V0 is 4 volt. Or you can apply superposition, right? So what is superposition theorem? With the voltage at inverting alone, it's minus R2 by R1 times of 2. So minus 3K by 1K times of 2, that is going to be minus 6. All right, minus 6. But due to this 1 volt, it is going to be 1 plus R2 by R1 times of 1. So 1 plus 3K by 1K, 4. So 4 minus 6 plus 4. Minus 6 plus 4, that's minus 2, right? It's minus 2. It's minus 2. What? 1 minus 3. I'm sorry. What is 1 minus 3? Right? 1 minus 3. I have to ask my son, right? 1 minus 3 is minus 2 volt. Right? Okay. 1 minus 3. Right? So it is actually minus 6 plus 4. Right? So please apply superposition as a homework. You take only one source at a time. You will get minus 6 plus 4 in this problem. Minus 6 plus 4. So that is going to be minus 2. See, the voltage at inverting is more, the effect of 2 volt is more than the effect of 1 volt here. So minus 3K by 1K times of 2, that is going to be minus 6. And this is 1 plus 3K by. So how do you apply superposition? Superposition as a homework. As a homework, I don't have space here. Apply superposition and yeah, after this I'll solve even by taking one source at a time. You should be getting the same answer. You can do it as homework. What is there? 2 volt, you ground it. So without 2 volt, without this 2 volt, what is the answer? Minus 3K by 1K times of 2. That is minus 6. You connect this 2 volt here at the non-inverting, then you get 4. So what is minus 6 plus 4? That's going to be minus 2. Right? Okay. How do you solve this? You can take, I told you, you can apply superposition theorem, or you can take one source at a time, or you can do by applying KCL, right? Yeah. Let's apply KCL. This current I1, I2, I3. What is the current drawn by an op amp? 0. We can have I4. This is, just see here, I can't put V1 and V2 here because those values are already here. Can I call this as VP? P for positive. Vn, n for negative, right? Just to, because if I take V1 and V2, they're already here, right? I'll take Vp and Vn, and Vp equal to Vn. Why Vp is equal to Vn? Because of virtual short. Virtual short. Vp equal to Vn because of virtual short, right? So now let me take this current as I1, I2, I3, and this is I4. And the current drawn here is 0. So you can apply KCL. Tell me I1 plus I2 plus I3 equal to I4 plus 0, right? So these are the currents entering here, and these are the currents leaving, right? I1 plus I2 plus I3, they meet here and they divide as I4 and 0. What is I1? I1 is going to be V1 minus Vp by R. I2 is V2 minus Vp by R. I3, V3 minus Vp by R is I4. I4 is Vp by R. Is Vp by R. So R gets cancelled. So what is Vp, by the way? We have Vp 1, 2, 3, and 4. 4 Vp is V1 plus V2 plus V3. So what is Vp? It is V1 plus V2 plus V3 by 4. By 4. Now I1, I2, I3 is done. We can have I4 here. So I4 is already there. Oh, I5, I6, I7, I8, and this is 0. So 5, 6, 7 equal to 8. I5, I6 plus I7 equal to 0 plus I8. So what is I5? What is I5? V4, V5, V6, right? So what is I5? It is V4 minus Vn by R. It is V5 minus Vn by R. It is V6 minus Vn by R. What is I8? I8 is Vn minus V0. Vn minus V0 by R. So how many Vn's are here? 1, 2, 3, 4. 4 Vn equal to V4 plus V5 plus V6 plus V0, or Vn equal to V4 plus V5 plus V6 plus V0 by 4. Now all of you, we have already got equation 1 here and equation 2 here. So now we know equation 1 is equal to equation 2. Equation 1 is equal to equation. What is equation 1? Equation 1 says that it is V1 plus V2 plus V3 by 4 is V4 plus V5 plus V6 plus V0 by 4. So what is V0? It is V1 plus V2 plus V3 minus of V4 plus V5 plus V6. If you apply superposition, could be still easier. It's okay. Yeah. Now, any name you can suggest for this? Any name you can suggest for this by looking at the answer, the final result. Any name you can suggest for this? Yeah, let me check. Any name? Did I get any names here? Yeah, very good. Some of you have got the answer. You typed it. Good, 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 good. Very good. Yeah. So we can call this as there's addition here, as well as there's a subtraction. So can we call this as an adder bar subtractor, right? Now, when is it a non-inverting adder, right? So if not, if V4 equal to V5 equal to V6 equal to 0, then the circuit is a non-inverting adder. Non-inverting adder. Why is it a non-inverting adder? Because V0 is V1 plus V2 plus V3. What happens if V1 equal to V2 equal to V3 equal to 0? Then it is an inverting adder. Inverting adder. Because V0 is minus of V4 plus V5 plus V6. So it's the same circuit. You can use it as an adder bar subtractor, or you can use it as a non-inverting adder, or you can use it as an inverting adder. Now, what if we don't have R here, but instead we have R, 2R, 3R, and 4R, 5R, like that, right? You keep changing, then the factor of multiplication will also change. You can change the weights. The weights, it's like the weighted resistors, right? You can change the weights associated with V1, V2, and V3. So suppose you want 2V1 plus 4V2 plus 6V3, something like that, right? So you can do it by adjusting the values of what? Resistors, right? Okay. Now, the voltage at non-inverting, if it is Vp, the voltage at inverting is Vn, right? So what is Vp by voltage division? You have V1 with respect to ground. But the voltage across, the voltage at the non-inverting terminal is Vp. By voltage division, Vp is going to be V1 R2 by R1 plus R2. But this is same as Vn because of virtual ground. Because of virtual ground. Now, the current entering is equal to the current leaving. So you can apply KCL. V2 minus Vn by R1 equal to Vn minus V0 by R2. Now substitute 1 into. Then you get V0 equal to R2 by R1 times of V1 minus V2. So any name that you can suggest for this, any name that you can suggest for this, the output amplifies the difference between the two inputs. Therefore, it is called a difference amplifier. Difference amplifier. The output amplifies the difference between the two inputs by a factor R2 by R1. Therefore, it is called difference amplifier. Now, what happens if R2 equal to R1 equal to if R2 equal to R1 equal to R? If both resistors are of same value, then V0 is V1 minus V2. Then the circuit is a subtractor. So how do you build a subtractor? This should be R, right? So you want a subtractor, everywhere it should be R, right? Then your output is going to be V1 minus V2. V1 minus V2. So if you want, you can have a subtractor also here after I finish this, right? So please, once you finish the class, you try to practice all of them. The same thing, you do it again, right? Once again, there's nothing wrong, right? Don't just go jump into new problems and keep trying them. Whatever we are doing in the class, you have to again repeat, right? The notes first. That's the first step any student should do. It might look simple, but still, right? Do it once again. There's nothing wrong. Okay. So how do we solve this? The voltage at non-inverting, if it is V1, the voltage at inverting is also V1 because of virtual short. If this non-inverting is V2, this end is also V2. And what is the current drawn by op-amp? What is the current drawn by an op-amp here? 0. Here also it is 0. So let's apply KCL, two KCLs. Oh, I don't know what this node is. I have to eliminate this. So because I don't know, what do we do if we don't know? We don't know. We'll call it Vx, right? So Vx, I don't know what it is, so I'm just calling it Vx. Now, please don't apply KCL at Vx, right? KCL at Vx, because once these problems are over, I will again have one or two problems on the current given by the op-amp. So don't apply KCL here because you don't know how much current the op-amp is giving, right, to set up virtual ground, right? So please apply KCL either at V2 because the current drawn by an op-amp is 0 and KCL at V1. That is enough because the two unknowns V1 and V2, so two equations, right? So V2 and V1, so you can apply KCL at V2 as well as V1. Don't apply KCL at Vx, right? Okay. Entering current is equal to leaving current. Entering current is equal to leaving. KCL. Tell me. KCL. Right now, we will also apply KCL at Vx for the other problems which I give you, where we are supposed to find currents, right? What is the current drawn by the op-amp? If you want, you can apply here also, but examiner has not asked the current drawn by an op-amp, so don't waste time applying KCL there, right? You end up getting current there. Now, entering is equal to leaving. So tell me, V0 minus V2 by R2 is equal to V2 minus Vx by R1. V2 minus Vx by R1. So what is Vx by R1? I don't want Vx. So we don't want Vx. So what is Vx by R1? It is V2 into 1 by R1 plus 1 by R2. So I'm bringing this V2 by R2 to the right side. And this is minus V0 by R2. So this is Vx by R1. Vx by R1 is V2 into 1 by R1 plus 1 by R2 minus V2 by R2. Okay. Now, let's have KCL, one more KCL at V1. This is KCL at V2. Let's have KCL at V1, right? This is the current entering here, is leaving, right? Entering, tell me. It's Vx minus V1 by R1 is entering, is 0 plus V1 by R2. Vx minus V1 by R1 is, yeah. So what is this Vx by R1? Vx by R1 is V1 into 1 by R1 plus 1 by R2. But we don't want Vx, right? We don't want Vx by R1. Oh, the first equation has Vx by R1 and the second equation also has Vx by R1. So thankfully, equation 1 is equal to equation 2, right? So what is Vx by R1 here? It is V2 into 1 by R1 plus 1 by R2 minus V0 by R2 equal to V1 into 1. V1 into also 1 by R1 plus 1 by R2. So what is V0? V naught is going to be 1 plus R2 by R1, right? So 1 plus R2 by R1 into V2 minus V1. Okay, so this is also a difference amplifier. It's also a difference amplifier, but the only difference is the multiplication factor. In the previous case, we had a multiplication factor R2 by R1 times of V1 minus V2, right? R2 by R1 times of V1 minus V2. But here in this case, we have a difference amplifier with a different factor of multiplication, that is 1 plus R2 by R1. 1 plus R2 by R1 is the factor of multiplication. But otherwise, both are difference amplifiers, right? But that is that is designed using a single op amp, right? But this is designed using two op amps. Oh God, where is this? Yeah. Okay, so the subtractor, I told you, subtractor is the same difference amplifier where all resistors are of what value? Same value. So we already know the answer. V0 is V1 minus V2, right? Let us prove by superposition theorem. Superposition. In superposition, we will take one source at a time, right? So first we will take V1 alone. V1 alone. When I take V1 alone, V2 is replaced with short circuit. Then how does the circuit look like? There's no V2, I'm replacing it by short. Am I right? So this node is, what is this node here? This node is VP. VP and VN both are same. All right. So what is VP? VP is going to be Vn into R by R plus R. It is V1 by 2. It is going to be V1 by 2. So what is the output now? It is 1 plus R2 by R1 times of VP. Or you can apply KCL here. Apply KCL. It is 0 minus Vn by R equal to Vn minus V0 by R. So what is V0? V0 is going to be, in the place of Vn, you can have V1 by 2 and V1 by 2 here. So V1 by 2 plus V1 by 2, it's going to be V1. So V0 is V1. V0 is V1. V0 is V1. All right. Similarly, with V2 alone, your V1 is replaced with short circuit. So this is a simple inverting amplifier. We don't have to calculate. This is V2. We have R here. We have R. Now, because op amp draws no current, this voltage is still 0. So it is V2 minus 0 by R is 0 minus V0 by R. So what is V0? V0 is minus R2 by R1 times of this. This is minus V2. So now, what is the total V0? Total V0 is equal to V01 plus V02. The first equation plus the second equation. It is V1 minus V2. The first equation says that V0 is V1 with V1 alone, and the second equation is minus V2. So this circuit is a subtractor, right? Is a difference amplifier when all resistors are of what value? Same value. If all resistors are of same value, then the difference amplifier converts to a subtractor. So what is superposition theorem here? The total response is equal to the total response is equal to the sum of individual responses, right? Taken one at a time, is it not? Taken one at a time. So we found that the total response is always the sum of individual responses. Yeah. Suppose if I ask you, find V0 and I0 give also, right? I0 given by the op amp. Op amp is ideal. Find V0 and I0. So I told you the op amp from the power supply, it has to modulate the current. It has to keep on changing that current in a fashion that the voltage at non-inverting almost equal to voltage at inverting. So to bring back the same 3 volts, it has to pump some amount of current I naught. So how much current op amp has to give in order to set up virtual ground? How much current op amp has to give in order to set up virtual ground? Right? So this is the non-inverting amplifier. We already know the output. So if this is 3 volt, this is also 3 volt. And what is output V naught? V naught is going to be 1 plus R2 by R1 times of 3. So this is something we already know. V naught is 1 plus R2 by R1 times of 3. So how much is this? 2 by 1 is 2 plus 1 is 3. 3 3s are 9 volt. 9 volt is the output. But we have to calculate even I naught here. I naught. So in order to calculate I naught is entering this node. So you can take 2 currents here. There's some current here, feedback current IF. There's some load current IL, right? So now tell me Kirchhoff's current law. The sum of currents that enter is equal to the current leaving. So KCL, I naught plus IF is equal to IL, or I naught is IL minus IF. I naught is IL minus IF. What is IL? IL is going to be V naught by 3K. And what is IF? What is IF here? 3 minus V naught by 2K. Now you have to substitute V naught equal to how much? 9. Therefore, I naught is 9 by 3K minus 3 minus 9 by 2K. 3 minus 9 by 2K. So 9 by 3K is 3 milli. 3 minus 9 is minus 6 by 2K. Minus 6 by 2K is minus 3. So it's plus. So 3 plus 3, it's almost 6 milliamp something, right? Just calculate. So op amp has to give this current in order to set up what ground? Virtual ground, right? So it's the job of op amp to give a current of 3 plus 3, which is equal to how much? 6 milliampere in order to set up virtual ground, right? And the current directions, it's your wish. I told you, instead of IF in this direction, you can take IF in the opposite direction, any direction you want, but please don't change the direction of I naught, because I naught is in the problem, and you are at liberty to take the other currents in your own way, right? In whatever way you take, Kirchhoff is going to take care. Your answer is not going to change, but don't change I naught, because I naught is something we have to find. The other branches, your wish. If there are 5 branches, 5 currents, it's your wish, right? So any direction you can take, your answer is not going to change, right? So similarly here, we are supposed to find I naught, and this is 0. So this node is also 0, all right? And you have V naught here. You can have entering current is equal to leaving, or you can take a current, this is I naught, you can have IL here, and you can have IX like this, right? IX. This is entering, these are leaving, like this. IX, but can op-amp draw current? No, the same IX will flow like this. The same IX traveling like this, right? Your wish, any direction you can take. Now, tell me, V naught minus 0 by 2K equal to 0 minus 3 by 1K. So what is V naught directly? Minus R2 by R1 times of V, minus 2K by 1K times of 3. It is going to be minus 6 volt, right? So your V naught is going to be minus 6. But let's apply KCL now, KCL. KCL tells that I naught is the entering current is equal to IX plus IL. IX plus IL. What is IX? It is V naught minus 0 by 2K. And what is IL? It is V naught by 4K. So it's going to be minus 6 by 2K minus V naught is minus 6 by 4K. Right? This is I naught. Please calculate the value, right? So 6 by 2 is minus 3, and you have 1.5 here. So 3, 1.5 is around 4.5 milliampere of current is going to flow. Now, all of you, the resistors we have chosen in such a fashion that in the previous example, the current that is given by op-amp was positive, 6 milliampere. That means op-amp is trying to source current. And in the second example here, the current I naught is minus 4.5 milliampere. It's not sourcing, it is sinking. That means the actual current in an op-amp is flowing in the opposite direction. Op-amp can source current or sink current, right? So the actual current is flowing in the opposite direction, but because the examiner asked I naught is still going to be minus 4.5. Yeah, good.
Is it done? How much time is left?
No.
Okay.
Close the door.
Okay. Is anyone asking doubt?
After this. They're able to see.
I'm here.
Okay.
Eagle. I washed my hands.
What happens if op-amp sinks current and sources current? See, op-amp's job is to see that it sets up virtual ground. The student is asking me, what do you mean by sinking and what do you mean by sourcing? See here, current, there is no question of current flowing in this direction or in this direction. Remember, current will always flow in a loop. Are you getting? It flows in a loop. If it flows in this direction, we are saying it is sinking. If it flows in the opposite direction, we are saying it is sourcing. But remember, current, or the basic idea is current always needs a closed path to flow. So suppose if I'm having a positive supply here, positive supply, and a network and some bunch of transistors here, right? There's a load. And here are some bunch of transistors, and I'm having a negative supply here. This is a load RL, right? This is V. Now tell me, we all know that current always flows from which potential to which potential? Plus to minus, right? Plus to minus. So if the current is supplied by the positive supply of the op-amp, positive supply, then the current is going to flow in this direction. Now this is called sourcing, source, or it is called pushing, right? Push. But if the current is flowing in this direction, it is called sink or pull. So to enable this, the last stage of an op-amp, has got something like this, right? If the upper transistor is on, it's going to source. If the lower one is on, there's an NPN and a PNP, some kind of a push-pull amplifier. So don't worry about that right now, right? So there's some kind of a construction inside. Your job is only to calculate the current, right? The current is positive, it's sourcing. If the current is negative, it is sinking. So don't worry, okay? So there's some kind of a construction here at the last stage. So if the current is flowing like this, remember it's given by this positive supply. If the current is flowing like this, remember it's given by this guy, right? So don't worry about that, right now, right? So the sourcing and sinking are called pushing and pulling. So but current is always in that loop, right? So this is pushing, pull, push, pull. This push, pull amplifier. There's an amplifier at the last stage, right? Push, pull. Don't worry about that. Yeah. So if you have a positive current, remember there's some work for the positive supply, right? If you're getting a current negative and the current is flowing in the opposite, so there's some, it has to something do with the negative supply, right? Negative supply and the transistor. An NPN and a PNP in the last stage. So don't worry about this right now. When we take up amplifiers, right, then you will realize that there's some kind of a construction inside. So that arrangement is there to take care. So you don't have to worry about what sort of arrangement is there inside. Just apply Kirchhoff's laws. You get positive, that's the answer. You get negative, that's the answer, right? The actual current is flowing in the opposite. find the ratio between the current and the voltage. That is called the input resistance. What is the input resistance? Rn seen at the non-inverting terminal, Rn. Calculate the input resistance of the amplifier. Okay. Now, while calculating the input resistance, remember you can have three ways of calculating input resistance. Three ways. One is the input resistance through non-inverting with respect to ground. Two, the input resistance through inverting with respect to ground, or the input resistance between the two terminals. So how do you know where you are calculating? It all depends on Ohm's law. What is Ohm's law? R equal to V by I. V by I. So V is the voltage source. Where you are connecting voltage source, there you are trying to find the resistance. Suppose you connect a voltage source, here. Suppose I have an op amp. You connect a voltage source here with respect to ground. Then it is the input resistance seen through this terminal. If you do V by I, what is resistance? It is V by I. Or if you connect a voltage source from here to ground, then it is the input resistance seen through inverting. There is one more input resistance called the differential input resistance, where the voltage is applied between the two terminals, and you're finding current. This is called RID. What is RID? It is the differential input resistance. And remember, there's one more also. This is 1, 2, 3. There is one more which I'm not going to tell you now. That's called the common mode input resistance. In common mode, what we do is we short both the terminals and applying voltage. So finally, what is resistance is V by I only. V by I, V by I, V by I, V by I is resistance. But where you are connecting that V will actually decide where you are finding. Here, the examiner has put an arrow only through plus. That means he is asking you to find the resistance with respect to ground. If he puts an arrow through the inverting, is only from inverting to ground. If he puts two ports like this, two lines, and there is an arrow in between those two lines, he's asking you to put a voltage source between the two terminals. That is the differential input resistance. And if you short both the terminals and apply, of course, this is a special case where you short and apply. That's in a topic called CMRR, common mode gain and the differential gain. We will see there, right? So there's a common mode input resistance is you short. So when you have two terminals, you actually have 4 ways of calculating input resistance. And remember, already op amp has another open loop input resistance inside. Okay, that is a device input resistance. But the network, you can have 4, out of which we are going to calculate only 2 now. 2. Input resistance at plus, input resistance at minus. Input resistance at plus, input resistance at minus. But the differential input resistance and the common mode input resistance in between the two terminals and shorting them and finding, we will see in a topic called CMRR, because there we want to know how well a differential amplifier can associate itself to amplifying our signal, and it want to reject the common mode noise. The noise happens to be a common mode devil, right? So if it has to reject the common mode noise, we have to calculate, all these calculations we have to do. But right now, it's not needed because the arrow is given between plus terminal. So it's understood that it's between the plus terminal and the ground. Now, let's calculate it. Let's calculate. So what we have to do is, we have to connect a voltage source V with respect to ground and draw the current. Tell me, what is a current drawn by an op amp? 0. So, by Ohm's law, Rn equal to V by I, it is equal to V by 0, it is equal to infinite. So I told you, how do you calculate input resistance? You apply a test voltage Vt, draw a current It, right? The ratio Vt by It, it is going to be the input resistance. The current drawn is 0, so the input resistance seen through non-inverting is infinite. That is why high input resistance, the amplifier is voltage control, High input resistance, the amplifier is voltage control, right? So how do you calculate input resistance here? You apply a test voltage here, Vt, find It. Now can op amp draw current? No, it's the same It here. Now you can apply KVL. Minus to plus, minus Vt, plus It into R1, plus It into R2 equal to 0. So Vt by It equal to R1 plus R2. This is also a gate problem. The input resistance is R1 plus R2 in this case, right? If there is no R2, the current flows through the op amp. So op amp draws no current. So even though you have R1, the input resistance is still infinite. But if you put R2 here, you're providing a path for that current to flow. And remember, these two resistors are in series now because there's no current flowing through op-amp. The total input resistance is going to be the summation, right? Yeah. How do you calculate input resistance here? You apply a test voltage VT, find current IT. According to virtual ground, this is 0. So IT equal to VT minus 0 by R1. So what is VT by IT? It is R1. So I told you, how is this circuit behaving? How is this circuit behaving? This circuit is behaving as if there is only R1, as if there is only R1, and the whole op-amp is virtually a short. It's virtually a short. You have VT here, there's IT here, and there's R1 here. Now just tell me what is VT by IT? VT by IT is R1, and this whole network is behaving as if it is a short circuit, right? So low input resistance, the amplifier is a current controlled amplifier, current control. And what is the value of current you're programming? It is equal to V by R1, right? So V by R1, so it's fine, right? So what is the input resistance now? It is only R1. Oh my God. Yeah, so that's it for today. We can have some time on the question answer session. Then we'll wind up, right? And please practice problems, practice. Oh, there's one more here missing. Apply VT, find IT. According to virtual ground, this is 0. No current will flow. IT equal to VT minus 0 by R1. So what is VT by IT? It is R1. R1 itself is the input resistance. Okay. Yeah. Yeah, tell me. Yeah, Venkat, please allow the students to talk. Venkat, please allow students to talk.
Already done, sir. Ask them to unmute and talk.
Yeah, you have to unmute yourself. Thank you, Venkat. Yeah. Tell me.
Sir, I have no doubt, sir.
Very good. Anybody else? Please practice. Anybody else? Nobody has doubts? I find hands being raised, but I think everybody's in a hurry to go home. Huh? Is there anyone there? Please unmute yourself. Unmute yourself. Venkat, what's the problem?
hello sir.
Yeah.
Sir, student unmute చేయమంటారా?
అవును.
Okay.
Students ki undi sir. Ask them to unmute and talk.
Oh, really? Can you unmute yourself? Or you can also do, Venkat, in case if they are not able to do. You can help them. Venkat, did you unmute them?
Undanడి
సార్ అది స్టూడెంట్స్ చేసుకోవాలి సార్ అది.
Avuna?
ఆ, ఒకసారి మీరే మీరే చెప్పండి సార్ స్టూడెంట్స్ కి.
Yeah. No, can you unmute yourself and have a, if you have any doubts, you can talk. I've seen around 35 students raising their hand, but nobody's talking. Okay.
Now ask them to unmute sir.
Huh?
Now ask them to unmute.
Yeah, now you can unmute. Yeah.
Hello, sir.
Yes.
Sir, would you please explain the duty cycle of a comparator again?
Duty cycle of a comparator. Yeah. I mean, this waveform, you have a problem?
No, how pi by 6 and this all came?
Okay, okay. See, this is a sine function, right?
Yes, sir.
Yeah. So sine will give you zero values at sine 0, sine pi, sine 2 pi, like that. And when sine is pi by 2, you get maximum. Am I right? This is a sine function. The function
Yes.
keeps on changing. But now I want the sine function to touch 3 at this point. Can you see the point here?
Yes, sir.
So I'm writing 6 sine t will touch 3 when the time is pi by 6. So this is pi by 6. So pi minus pi by 6 is 5 pi by 6 here.
Okay, okay, sir.
Are you getting?
Yes, yes, sir.
Yeah, good.
Thank
Yeah.
you, sir.
Yeah. Yeah, anybody else? Anybody else?
Hello, sir.
Yeah.
Sir, I have doubt in this finding I naught, sir. The second problem.
In finding I naught,
Yeah.
op amp, right?
Yeah, yes, sir. You have taken the direction in reverse, right?
I naught, I have not changed I naught direction. I have
IX,
only-
IX direction.
IX, your wish, wherever you want, you can take. Yeah.
Oh, okay, sir.
Because the other branch, suppose we have 5 branches in a network,
Okay.
and in branch 3, you want to find current. The
Yes,
other
sir.
4 branches, it's at your liberty. You can take, because accordingly you will apply Kirchhoff's law, no? Your Kirchhoff's law accordingly will say entering equal to leaving. So your I naught is not going to change. Are you getting?
Okay. Yes, sir. Yes, sir.
Yeah,
Got
yeah.
it.
Good.
Thank you, sir.
Yeah. Yeah, anybody else? Anybody else? Anybody else? Anybody else? Maybe today op amp was a simple topic for you, so you were comfortable, right? 1 plus R2 by R1 minus R2 by nobody's speaking. Huh? What happened? You're not able to unmute? Can you message me? What's the problem?
Hello, good evening, sir.
Yeah, good evening.
Sir, the actually problem is once the co-host has to unmute, then only we can mute or unmute ourselves. I think that's the
Okay.
now I think the co-host has unmuted, so there was a prompt appeared in my screen, so I unmuted myself. Now I can mute or unmute myself.
Now no issues, sir. Now no issues. You can unmute and you can talk.
Yes. Okay.
Okay, yeah.
Thank you.
Yeah,
Sir,
fine. Anybody has doubts?
Sir, I
Hello,
had a doubt actually.
Yeah, tell me.
Sir, in the initial, I mean, in the start of the lecture, when you are explaining negative feedback,
Yes.
you took some table kind of thing where you did some iterations, no, sir?
Yes, very good.
Sir, in those iterations, I had a feel that because the gain was low, that's why we were not getting.
Yes. Very good. Because the gain was low, we were able to predict it.
Yes, sir.
Otherwise, if you take gain 10, I actually tried 10 as a student. It
Yes.
took me almost a big chart. Because
Sir, if the gain is
or iteration.
gain is large, then for whatever small value we'll have of V1 minus V2, then
It's going to shoot up.
Yes, sir. It will going to shoot up, and then it will have plus VSAT or minus VSAT, no, sir?
No. If the gain is 5 or 10, it doesn't matter.
Just a moment. Yes, sir.
See, this is a good point. Everybody should listen here. What he's trying to say is, if the gain is high, two things can happen. One is, gain is always output by input, V naught by VD.
Yes.
So his point is, if gain is very large, two things can happen. One is, your V naught can shoot up. Two, your VD can come down. So there are two conditions. Because this gain is high, right? Gain is high.
Yes.
The gain is in P by Q form. Now what happens is, if you don't give feedback, your V naught will shoot up. Your V naught is going to shoot up to infinite. You're right.
Yes.
But in negative feedback, your V naught will not shoot up. It become a tracking device. Your VD will actually converge to 0. Are you getting?
Yes, sir. Yes, sir.
Yeah. Gain is output by input. So remember, in negative feedback, input will become less.
Input.
Input will become less.
Okay.
But the same high gain amplifier, if you give positive feedback,
yes,
then your V naught will shoot up to infinite. It's an open loop or positive feedback. Your V naught will shoot up because it's the same device you are using for negative feedback as well as open loop as well as positive feedback. Then how do you define this factor? Gain is output by input. Output can be more or input can be less. So in this occasion, as I kept on increasing my gain, what is happening? The error between the two terminals will converge.
Yes.
Yeah. So in positive feedback, which I will explain later, or open loop, error VD diverges, and V naught is at plus VSAT. What you said is absolutely right?
Yes.
But in negative feedback, what is happening is the error VD converges to zero, and your V naught is going to lie between minus VSAT and plus VSAT. Are you getting what I'm saying?
Yes.
Very, yeah.
Thank you very much.
Yeah. Anybody else? Anybody else? Anybody else?
Hello, sir. Audible, sir?
Yes. Tell me.
Sir, in 45th slide, can you, sir, please open that?
Yeah. 40.
45.
Yeah. Specs. This one?
Yeah. Sir, in that common mode, why you have changed the direction of the terminals, sir?
Here, the common mode I have not explained. I'm just telling you. Any problem with RN?
No, sir, no.
No problem.
Not
Yeah,
I.
common mode gain, if we have to short, it's not shorting, we have to apply a common voltage to both the terminals. How will you apply? Say I have to apply a common voltage to, I have to give V here and V here. Instead of giving V, we will just short and give for
Okay.
common mode gain. Are you getting?
Yes, yes, sir.
Yeah. We'll do this calculation in a topic called CMRR. Okay?
Okay, sir.
Yeah.
Hello, sir.
Yeah.
Hello.
Yeah, tell me.
Sir, in the duty cycle problem, we are considering the T1 period only for the pi by 6 to 5 pi by 6, right?
Yes.
So, why, sir? Why like that only in that period it's on?
No, it's gone high there, right? It's
Okay,
only the ratio between the logic one to the total time.
Okay, so we are considering only logic 1 as high,
Yes.
and only that part we are considering on time.
On time logically is logic one. Yeah.
Because for some circuits, we can consider the negative time
Yes.
also as on period, right? So that's
You're
why.
absolutely right. Yeah.
So in this case, we are considering only the positive high as the on time.
Yes. You're right.
Okay, sir. Thank you.
Yeah. Good.
Hello, sir.
Yeah.
Sir, 25 F, sir.
20?
5.
25. This one?
Sir, can you please explain this concept once more?
Yeah. See, if I have 1 volt with 1 ohm in an open circuit, I have explained this in my first class with 2 resistors. Do you remember R1 and R2? I connected R2 in the place of V actually. I connected R2 in the place of V. Okay, I'll explain. Is there? Yeah. Suppose I have a voltage V. There are 2 resistors R1 and R2. Am I right?
Yes, sir.
Yeah. Now, what is the voltage V2? We all know that V2 is going to be VR2 by R1 plus R2. Am I right?
Yes, sir.
Or it is going to be V by 1 plus R1 by R2. 1 plus R1 by R2 is V2. Now the question is, I want to remove this R2. I want to make R2 infinite. If I make R2 infinite, will I get this circuit? Infinite means open circuit. Are you getting?
Yes, sir.
Now, you substitute R2 equal to infinite in this equation. What do you get? R1 by infinite. Anything by infinite is 0. 1 plus 0 is 1. Your V2 will be V. So that means in an open circuit, complete voltage will be manifested.
Okay, sir.
Are you getting? But what is 0 is, can current flow in an open circuit? No, current cannot flow. Is it not? So current needs a closed path. So current is 0, but the whole voltage is V. Are you getting?
Yes, sir.
Very good. I think the other one, you don't have a problem, no? There is simple V and R with a short.
Yes, sir. No problem.
Yeah, okay.
Thank you, sir.
Yeah, good. Next.
Hello. Good evening, sir.
Yeah, tell me.
Sir, I'm small doubt in 39F.
89.
39.
39.
Then 38. Where we were having 2 op-amps in a single question.
Yeah, okay.
Sir, I did a different approach. Could you say whether it is correct or not? I wrote V1 in terms of Vx using voltage division rule.
You wrote V1 in terms of Vx. Okay.
That is V1 is equal to Vx. I mean Vx equal
Vx into R2 by R1 plus R2.
Yes, sir.
Very good. That is exactly what we have got at equation 2, no?
Okay, sir. Yeah, got it, sir. So I thought instead of writing these 2 KCL equations, I just did I is equal to I.
You're absolutely right. That is exactly what we have in equation 2. Yeah, good.
Oh, okay, sir. And even in the next question, we were calculating the IF, no, sir, the feedback current in the next 2 questions.
Yeah. Okay.
Yeah, where the current which is entering the negative port is equal to the current which is IF, no, sir.
Current. Can you tell me the page number, please?
42F, sir.
Yeah. Tell me.
Yeah, here we were again calculating IF, writing this equation, no, sir. The same current which is entering into the inverting terminal is equal to IF, right, sir?
Inverting terminal does not draw current.
I mean, the current.
Yeah. This current. Yes. This one, right?
Yeah. Yes, sir. Yes.
Very good.
Yeah.
So it's minus 3 by 1K, minus 3 milliampere. You're right.
Yeah. So I was confusing that should we find it or it is the same current?
It is the same current. So it's legible here. What you have done is absolutely correct.
Okay.
You say that it's the same current. So you took minus 3 by 1K. So it's minus 3 milliamp and directly substituted here.
Yeah. Yes, sir.
Very good. Very good. Very good.
Sir, and the
Good
way
try.
you explained negative feedback was so good, sir.
Thank you. Thank you.
Like I could see how actually op-amp was behaving.
Yes. I mean, as if it has got some life and it is doing that struggle. Are you getting?
Yeah.
Very
mean,
good. Very
see
good.
the real struggle for it to attain the final value.
Yeah. Very good. Very good. So yeah, this is not like a GPS system where suppose you want a person to go from here to the airport, right? With his eyes closed. He just ties his eyes and there's no GPS. So what will he do? He'll first go and hit the wall.
Yes.
Blood
Sir.
will come. Then he'll realize this is not the direction. He'll go into the other direction, hit another wall. So finally he'll find a path and, somehow, if you want to go, you're in a house with all your eyes closed.
Yes.
And there is only one door to open and you have to come out of that house. Then what will you do? You'll hit every wall and finally you come out. Yes or no?
Yes, sir.
The same thing the op-amp is probably doing, right? It's going to every point. Very good, very good, very good.
Thank
So
you,
you have
sir.
enjoyed.
Yes, sir. A lot.
Good. Yeah.
Hello, sir.
Yes.
Sir, in next page 43F, sir.
43F.
Next page, sir, 43F.
Yes.
Sir, once explain changing the direction of IX.
Yeah. See, IX you can
Hello?
take in whatever way you want. See, the same problem, you take IX in the previous direction, opposite direction, and then solve the problem. Your answer is not going to change. Are you getting?
Sir,
Why?
sir, once explain that one, sir. I am unable to.
Acha, you want me to explain KCL or you want me to explain why that direction
Yes,
is like
sir. KCL.
Oh, very good. Very
By
KCL.
changing
See,
the direction, once you check.
see, direction you can take as you wish.
Okay,
See, I'll tell you. Yeah, I'll give you. See here. Suppose I have a current I0 here, and it has got two branches. Are you getting? I0,
yes, sir.
two branches. I0, two branches. I0, two branches. Okay. Now you tell me if I take
Okay, sir.
IX like this, IY like this, how will you apply? If I take I1 like this, I2 like this, how will you apply? If I take I5 like this, I6 like this, how will you apply? I8 like this, I9 like this, how will you apply? However you apply, your answer is not going to change. Yeah. How? Tell me in the first case, what is I0?
Sir, in the first case, I0 is equal to IX plus IY, sir.
Very good. I0 is, let me write, IX plus IY. Yeah.
IX plus
And you will
IY.
calculate it. Yes. In the
Yes,
second
sir.
case, here, entering is
IC
leaving.
plus I5 is equal to. Yes,
In
sir.
the second case, this one,
IC plus I5 plus I6. Acha, this one.
this one.
I0
What you
plus
write?
I1 is equal to
I0,
I2, sir. Plus I1 is equal to I2, sir.
I0 plus I1 equal to what?
Is equal
I2.
I2, sir.
Are you getting? But what is
Yeah.
I0 here?
Yeah,
What
this
is
I
I0?
know.
What
I2
is I0
minus
here?
I1, sir.
Huh?
I2 minus I1.
Very good. I2 minus I1. But in the previous case,
Yeah.
What is I0? IX plus IY. Can you see?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Yeah. Can you see that this IY and I2 are same? Can you see that this IY and I2 are same?
Yes, sir. Yes, sir.
But can you see that IX and I1 are in opposite direction?
Yes, yes.
Because they are in opposite direction, there is a negative sign. Kirchhoff has taken care.
Okay.
Are you getting?
Yes, sir.
So a
sir,
student
yes.
one will be doing upper, he gets a positive sign with this direction. Student 2 takes the other direction, changes his direction, but there is a negative sign. What is minus of minus will again become plus. So both
Yes.
answers will remain what?
4.5.
Yeah, both answers will remain 4.5. It is not going to change. Are you getting what I'm saying?
Yes, sir, but I am getting plus sign, sir.
Acha, you're getting plus sign. Did I make a mistake there?
Yeah. No, I am saying, sir, once I explain, I am having little bit confusion there.
Please tell me the page number once again.
43F, sir, I think.
43F. 43F. Yeah. So let me explain this. Entering current is
Yes, sir,
I0.
explain.
Leaving current is Ix plus I1. Entering current is I0. Leaving current is Ix plus IL. So I0 equal to Ix plus IL. Is it okay? What
Yes.
is Ix?
Yes, sir.
What is Ix? Ix is the
Ix
current
is-
in this direction, which is V0 minus 0 by 2K. Plus
Yes, sir.
IL. IL is V0 minus 0 by 4K.
Yeah, yes, sir. This I understood, sir.
Now you substitute, you'll get the answer.
Okay, sir.
Where you have made a mistake, I have to see. Small,
No, sir, I am
small,
saying
slight
just-
mistake you have done.
No, sir, I am just saying reverse the direction of the Ix, sir. In the
However,
previous
you reverse-
problem we have
yeah.
taken, na, sir.
Yeah, it will still be same answer. You want me to reverse the direction and again explain?
Yes, sir. Yes, sir.
Yeah, okay, I'll reverse the direction Ix. Okay, I'll put Ix in this direction. Now, what you have to write is I0 plus Ix, I0 plus Ix is equal to IL, you have to write.
Yes, sir. This one only.
So I0 is IL minus Ix, you have to write.
Yes, sir.
So IL is same, but Ix is in the opposite. So you have to write 0 minus V0 by 2K.
Yes, sir. Same.
But here it is V0 minus 0 by 2K. Here there's already a negative sign. Negative of negative will become positive again. Same answer, no?
Yes, sir. But the plus and minus changes, no, sir, here.
Yes, my dear, there is a minus Ix here. So let me put minus here. What is Ix? 0 minus of V0 by 2K. Minus of minus
Yes,
is
sir.
plus. Plus V0 by 2K is
Yeah.
already here, no?
Okay, okay.
Now you got it. Am I right?
Yes, sir. Sir.
Yeah,
Yes,
good,
thank
good,
you,
good,
thank
good. Yeah, it's okay, it's okay.
Hello,
Yeah.
sir.
Yes, tell me.
Sir, can you differentiate between positive feedback and negative feedback?
Yes, I will explain when I take up positive feedback
Can you
circuits.
explain the difference?
Yeah, I will definitely explain. Just before taking up Schmidt trigger, I will show you, I will put a table and show you the behavior of the op amp, both for negative feedback and positive feedback. I will explain there. Are you getting? See, simple. In the previous, in negative feedback, we have seen the increase, next iteration will decrease. The decrease will again increase. But in positive feedback, the increase will increase, will increase, will increase, will increase, will increase until it shoots up to plus VSAT. Or if it is decreasing, it keeps on decreasing and decreasing and decreasing and decreasing until it shoots up to minus VSAT. Are you getting? This scenario, you want me to explain right now, positive feedback? Or can you wait till positive feedback class? Hello? So if you want, I can explain here. See here. In positive feedback, when you apply plus here, when you apply plus terminal here, this is V0, this is V1. If V0 increases, V1 will increase. If V1 increases, what is VD? It is V1 minus V2. V1 minus V2. If V1 increases, your VD will increase, which will further increase V0. Positive feedback. Now you tell me what will happen in this scenario. 1 millivolt will become 5 millivolt, will become 10 millivolt, will become 1 volt, will become 2 volt, will become, it will go iteration or iteration or iteration or iteration or iteration until this output will become plus VSAT. So this is the positive feedback structure. Are you getting? Is anyone there? Okay.
Hello.
Yeah.
Audible, sir?
Yes, audible. Tell me.
Sir, page number 38F.
38.
Yes.
38. Yeah. 38. This one? No. 38. Yeah.
Yeah, sir, here both the diagrams are same only, na?
Which diagrams?
Both the op-amps are configuration is same only, na, sir?
This configuration is same.
Means just go to next page, sir, 39. We are getting answer as 1 plus R1 by R2.
R2 by R1.
R2 by R1 into V2 minus V1.
You're right. Acha, you want to apply superposition theorem for this? Yeah, you can apply. You can apply. You want to take V1 alone, then you will get minus of 1 plus R2 by R times of V2, V1. And if you take V2 alone, you'll get 1 plus R2 by R1 times of V2. Yes, you can do it.
Okay.
Yeah, you can try actually as a homework. Why don't you try this? You short V2 with V1 alone you find, and with V2 alone you find. And what you said is absolutely correct. The whole structure of two op-amps put together is behaving as if it is a single configuration, 1 plus R2 by R1.
Right.
Yeah, good.
That 1 plus R2 by R1 is because of since we are using non-inverting amplifier, because of that.
Exactly. Because the input is given to plus terminal. You're right.
Okay. Sir, page number 42.
Page number 42. Yeah.
Just a second. Sir, here, since we told that op-amp is not drawing any current, so how is it possible that it is delivering current?
Yeah. See, op-amp draws no current at the input terminals. Am I right? Because at the input terminals, we'll connect the input impedance is very high. Even if you connect a microphone, there's a very, very small current that is coming from the microphone. But output, it has to amplify, no? If op-amp takes no current and gives no current, then what is the purpose of an op-amp? You want your cell phone to work. There is a battery and you want an amplified version of the output. Am I right? There's an amplifier at the microphone. Because of its high input impedance, it is not drawing. But it has to drive the speaker, no? Op-amp output has to be there because output port, you are getting an amplified version of the input. Are you getting what I'm saying? These are all amplifiers. These are amplitude trackers. You give a small signal, the same thing they will track and amplify it in a big fashion. See here. Okay, let me give you an example. See here. In this problem, I am giving you 0.2 sin t. 0.2 sin t. All right.
Right.
This is 0.2 sin t. This is 9K. Oh, this thing has come again. Mirror. I've learned from you. I struggled a lot actually. Layout. Mirror. Yeah, this is 9K. This is 1K. Now, what is V0? V0 is 1 plus 9K by 1K times of 0.2 sin t. Am I right?
Right.
Now, this is 2 sin t, V0. So, if you sketch why this is called a voltage amplifier, Vin is 0.2 sin t. The peak is only 0.2.
Right.
But output, it has to pump a larger amount of current because the output is 10 times of this signal.
Right.
Are you getting? When the input reaches 0 to 0.2, the output has to run. So just now, the other student was telling, sir, now I've understood the struggle of an op-amp. So the output has to run by pumping a large amount of current to 2 volts. Because when it goes 2 and then you backtrack, you get 0.2 here. And then the op-amp stops. I've tracked this 0.2. The moment this 0.2 becomes 0.1, what will happen when this 0.2 becomes 0.1? This fellow has to reach 1 volt. 1 volt. And then when it comes to 0, of course, it is at 0. When it goes to minus 0.1, it has to reach -1. When it's minus 0.2, so there's always a struggle going on at the output, and that amplified version of the output is only because of what? The current that it is pumping through the load.
Okay.
Are you getting?
Got it,
Yeah,
got
yeah,
it,
yeah.
sir.
Good.
Sir, in Miller effect, you told we applied it for ungrounded resistor or capacitor.
Yes. Because they only experience V1 minus V2, no? Grounded is there means already zero.
Miss, can you just explain where it cannot be applied?
Where you can apply it wherever you want, but it's an approximation. You don't get the exact answer. See, the point is, when you are calculating input resistance, just now we did, all these resistors are feedback resistors only, no? See, for input resistance, did I apply Miller's? See, R2 is having Miller effect. Can you see?
Yeah.
R2. There's between input and output, no? Ungrounded. Here R4 is having Miller effect. Can you see?
Yeah.
So any resistor that is ungrounded, it is stuck between input and output. You can apply Miller's. But the point is you are getting it in an easy fashion, right? So please apply Miller's only when the circuit looks complicated. If you are able to solve it just like this, please don't apply Miller's and complicate. Because moreover, Miller will give you only approximation. Are you getting?
Right, sir.
So next class, I will apply. Next class when I come, I am going to apply Miller effect even for op-amp. Provided the op-amp has a finite gain, I'll show you the Miller effect problems. Just remind me. If I forgot, please remind me. Just give a message there, right?
Sir, which book should I refer for analog?
Good. See, if you see Sedra and Smith, the book is almost 900 pages, but only 2 or 3 chapters are important for us. Because if you study BJT, one chapter itself, they will cover all what is necessary.
Okay.
So hardly even if the book looks bigger, there are hardly 3-4 chapters. That's it. 4 chapters, I think. 4 chapters. If you study, the whole syllabus is covered. But generally, student, in spite of saying this, but the moment they find that book, they find, oh, this is very big. It's a handbook. But only 4 chapters. That's it. One is BJT, complete BJT problems, DC and AC analysis. Next one is MOSFET problems, DC and AC analysis. And the 3rd chapter is the differential and current mirrors of BJT and the differential and current mirrors of MOSFET. In fact, if you see the new syllabus, these are the only covered. So 4 chapters are enough.
It will cover DC syllabus as well.
Everything. Even if you show me any book, the same 4 chapters, they will split it into 10 chapters and write.
Right.
So 10 chapters they will write. DC analysis, 1 chapter, AC, nothing. Everything will be there in that single chapter. He will start from DC analysis, go to AC analysis, and AC analysis, he will do all the calculations.
Sir, is one helps you good for analog?
5th edition. See, I follow old 5th edition. The reason is 5th edition solutions are also in the internet, and 5th edition is written by Sedra and Smith. After that, what they've done is I think 7th or 6th, 7th edition. Some great professor, IIT professor, is no more, but he has abridged it. He took that and he shuffled the chapters.
Okay.
First chapter he made it 4th he made it 3rd, like that he shuffled. So I'm following the original version with 5th and before 5th edition.
Okay.
Same content, not much change. New editions and the old edition. You can follow.
Okay. Thank you.
Yeah. Anybody else? Anybody else?
Hello.
Yeah.
Yeah, good evening, sir. Sir, can you explain source and sink? Sir, my internet was gone.
Can you explain what? Come again?
Source and sink.
Yes. See, the sourcing and sinking, I was telling them that they are big terms you use. current is, there is no current that is going to source or sink, but the current will always flow in a loop. If current flows, suppose a current is there, it is flowing from A to B in this direction. We call it sourcing. If it follows in this direction, we call sinking. But current is not going to flow like this, it is flowing in a loop. So I have mentioned something like this. Suppose if I have an amplifier like this, which has got a load here. An amplifier, and it has got a, load here like this. This is plus V and minus V. So op amp has got two supplies, plus V and minus V. When the upper supply is on, the current will flow in this direction because current always flows from plus to minus. When the lower supply is on, this minus plus, the current will flow in this direction. Are you getting? So there is an arrangement inside an op amp where that arrangement is called the push-pull arrangement. It's called the push-pull arrangement inside an op amp. It's called a push-pull arrangement inside an op amp where if the upper transistor is on, the current will push like this. If the lower one is on, it is going to pull like this, push-pull. It is source sink. So you can call it sourcing and sinking, or you can call it pushing and pulling, right? This is something I will explain in BJT, I said.
Okay. Sir, in RN also you said once we can take inverting, once we can take non-inverting source.
Yeah, based on where he gives the arrow. If the non-inverting is
what if
grounded,
we have both sources, sir?
No source will be given. Only a port will be given. You have to connect a source, no?
Yeah. What if there are two sources, sir?
If there are two ports and none of them are grounded, and he puts them an arrow in between, then it is a differential input resistance. You have to connect in between. In between you have to connect. Then it is not RID, it is RID. What is RID? It is a differential input resistance. The resistance seen by the source between the two terminals, right? But generally he gives like this. He connects non-inverting, inverting to ground, and he puts like this. That means you have to connect from here to ground only through plus terminal.
Yeah, that second one only without converting non-inverting, inverting to ground, inverting to other supply. What will happen, sir?
Inverting to other. Yeah, that's what I'm saying. Source, no, whether he gives, there is no question of connecting source. You have to connect the test voltage, no? Resistance is V by I. It is you who has to connect the source. He will not give.
Okay. So,
he will not give 2-3 sources and confuse us. That is a wrong question.
From slide 44, sir, I'll take the screenshots.
Yeah. 44. Okay.
I lost my internet.
Yeah.
Yeah, next ones.
Yeah, good. Anybody else?
Yeah, from 44 you show, sir.
Acha, you want me to show all this?
Yeah. Yeah, next one.
Anybody else who want to ask, they can ask.
Yeah, next one. Next one.
Yeah, this is the last one.
Yeah, thank you, sir.
Yeah.
Hello.
Yeah.
Sir, in that open circuit condition where the voltage at the terminal, can you draw that figure once? One voltage source and a resistor and the open circuit. So the entire voltage will be dissipated at the
Yes, manifested at the output, yes.
So then there won't be any voltage at the R1?
Yes, the R1 voltage is the current flowing through R1 multiplied by the resistance, Ohm's law.
Okay. So current is zero.
V equal to IR.
So current is zero.
Flowing through R1 is zero.
So there won't be any voltage across R1 then?
There is, yes, you're right.
Okay, sir. That's thank you.
Good. Anybody else?
Hello, sir.
Yeah.
You said that
Hello.
applicable in cases of that. Hello.
Hello.
Yeah, tell me.
Hello, sir.
Applicable on inverting amplifier.
Yeah, there
Hello.
is some disturbance. Yeah, tell me.
Hello, page number 25, sir.
25F. Yeah, 25F.
Sir, can you explain the amplifier thing, sir? I understood short circuit and open
Very
circuit.
good, very good. See, when I connect a transducer here at the non-inverting terminal, which is say 1 volt with 1 ohm, because every Thevenin equivalent you can draw it as not an equivalent. We don't know whether it is in voltage or in current, yes or no. So 1 volt with 1 ohm I have connected here. But what is op amp doing? Op amp draws no current at any of the terminals. So the current here is 0, and it is sensing that complete voltage 1, which is 1 volt, and the current here is 0. So from the transducer, see, you should think with respect to the input. What input will think? When the moment you connect it, no current is flowing from that source.
Yes, sir.
Are you getting? See, you should ask this 1 volt, right? What do you see there? What this 1 volt will say? Are no current is coming from my source. Maybe that fellow is this big op amp fellow is like one open circuit is there, because he is not drawing current. But the same 1 volt with 1 ohm, if you connect here, this fellow, you will think, complete 1 ampere you are drawing from my source. Maybe this 1 volt with 1 ohm, that means that this fellow is like a short circuit. He's drawing complete current from my source. So when 1 volt source delivers 1 ampere, he thinks that there's somebody who has shorted there, right?
I didn't get it, sir.
Okay, see, fine. Forget about 1 volt and 1 ohm.
Yes,
I am
sir.
having a microphone here. I'm having a microphone here.
Okay.
Now, this microphone, when I connect it to a non-inverting, it is found that there is a signal, there's a voltage signal here, some voltage signal here, but the current here, if you put a milliammeter or whatever microammeter, the current is 0.
Okay. Yes,
But
sir.
the same microphone, you connect it here. The same microphone, you connect it here.
Okay.
It is found that this voltage is always what? 0.
0.
There's a maximum current that is flowing. Here there is no current, but here
Okay,
there is
yes,
a
sir.
maximum current flowing. Then how will
Okay.
you explain this? How will you explain this? Then I have taken that simple diagram and I'm telling you that there is a short circuit at the maximum current is flowing here, but here there is a maximum voltage that is manifested, current is 0.
So it is the first one is acting as like open circuit and second one.
Yes. Now you got it. Yes.
Sir,
Current 0 means open circuit. Current 0 means open circuit.
Sir, can you explain the concept of virtual ground again, sir?
See, virtual ground, I was mentioning that if you have an op amp whose gain is A, and here you connect a voltage divider with some beta here, and you apply a voltage V1, I have shown that this V2 is actually beta times of what? V0.
Yes, sir.
And this V0 is A by 1 plus A beta times of V1. So V2 is V1 by 1 plus 1 by A beta. So I have taken some values. I have shown that if A beta is very large, as the A beta keeps on increasing, the op amp will finally come to a point where this V2 is almost equal to V1. The voltage at non-inverting will settle down at voltage at inverting. This is something called virtual ground. And this we have seen, if you go back home and see the table, first I have taken A as 1, then I put A as 10, then slowly when I increase A, 1 by A beta became 0. This whole factor, because A beta is larger. What is 1 by A beta? Very, very small. Then your V2 is almost converging at V1, no? It is a phenomena. See, why V2 is V1, that is not the debate here. The debate here is, because V2 is V1, how are you going to explain that phenomena? Are you getting?
Yes, sir.
Whether we like it or not, V2 is V1. But there should be a faithful explanation, right? Why V2 is not plus Vsat? I made a point. Why V2 is not minus Vsat? What happens if V2 is not V1 and any other value? Any other value, if it is there, it is restless. It keeps on changing it. If V2 becomes almost equal to V1, that is where the op amp is becoming stable.
Okay.
Are you
So
getting?
this, yes, sir.
Yeah,
So
yeah,
this virtual ground is applicable only for the negative feedback,
yes,
sir?
yes, you are absolutely right. Only negative feedback.
Okay, sir.
Yeah, good.
Thank you, sir.
Yeah.
Sir, 30F problem.
38.
30F. Second problem, find V naught.
If, yeah. This one?
No, sir, died.
This is 30, no?
29F.
This one?
No, sir. Died.
Okay. 28.
Just before 27.
This one?
Yes, sir.
This
27.
one?
Yes, sir.
Yeah, tell me.
How is it T volts? Like we have a resistor in between, then how can it be 3 volts?
Yeah, that's what I'm saying. When no current is flowing, this is like an open circuit. You have 3 volt. You have a resistor 1K. Suppose, your imagination is, suppose if there is a 1 milliampere current flowing, 1 milliampere. 1 milliampere into 1K is 1 volt. 3 minus 1, you should have 2 here, no?
Yes, sir.
If there is 2 milliampere current flowing, 3 minus 2, it has to be 1 volt.
Yes, sir.
But there's a current 0 milliamp, 0. So what is this voltage? It is 3 minus drop. So this voltage is going to be 3 minus drop. What is a drop? 0 into 1K. So 3 minus 0 into 1K, it is how many volt? 3 volt, no?
Okay, sir. Got it. Thank you, sir.
Huh?
Thank you, sir.
Yeah. Good. Anybody else? Yeah, what shall we do? Can we wind up? I'm feeling sleepy.
Hello, sir.
Yeah, tell me.
So, can you explain the zero crossing detector, sir? When to use and how to use, sir?
Okay. See, the name zero crossing detector, it tells that whenever the sine wave is crossing 0, the output should give you an indication. That's all. It is a normal detector. It is a normal comparator. The name, don't get worried about the name here. If one end is grounded and the other end is V in, now what will be your V naught? Whenever voltage at plus, if V plus is greater than V minus, what is the output? Plus V sat, no?
Plus V sat, yes, sir.
Yeah, so this V minus, if I make 0, it is a zero crossing detector. So this V plus is V in, and V minus is 0. If V in is greater than 0, then your output is plus V sat.
Plus V sat.
That's all. This is a zero crossing detector. So whenever your sine wave crosses above 0, the output shoots to plus V sat.
Yes.
Yeah. Now, if V in is less than 0, your output shoots
minus
to
V sat.
So now, if you give a sine wave like this with 0, then whenever it crosses above 0, there is plus V sat. Below 0, minus V sat. Good. That's all. You're right.
So today, starting question duty cycle, no, sir. You can say with a different questions, sir, like with a different input.
With a different input in the sense, you want me to change that input?
Yes, sir.
Change the input. What input you want? We can calculate, no? Okay, let me change the input. What if this is 8 sine t and this is 4 volts? Same answer you will get, no?
Yes, sir. Like 8 sin t, we can replace by cos also, no, sir?
Yeah, sine or cos, it doesn't matter.
Okay. we'll get the same answer. Like
Yes, yes, yes,
uh,
yes.
this 2 pi will be the old cycle, no sir.
Yes, 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 yes. You can sketch. Even you can have a triangular input and then a DC and then calculate also.
Okay, sir.
Okay.
So here in adder,
Ah.
when we have 3 inputs, sir.
Hmm.
3 inputs like
Yeah.
1 volt, 2 volts, and 3 volts. You have
Yes.
said that you can add it and you will get the answer. But
Yes, yes.
my thought is that can we take one higher voltage, sir? Only one higher voltage and calculate it. Not
We can do it, but the summation of the voltage should be less than your plus VSAT.
Okay.
Whatever the voltage at output is there, in all the problems, see, that's a very valid point you have made. Can we keep on increasing that voltage? Yes, but only till a point where the output is less than the saturation. You cannot give, 50 volt, 1 volt, 2 volt like that, when the supply is only 12.
Okay.
Okay.
If if a VSAT is 12 volts, sir.
Yeah.
Then we have the inputs of 1 volt, 2 volts, and 3 volts. My thought is that not to take all the 1 plus 2 plus 3. My thought is that only take 3 volts. That is the
Yeah,
higher
3 plus
voltage.
3 plus 3, you take 9 volt, you will get what is there.
Then we'll get the different answer. Okay, I got it.
Okay. Good.
So one question, sir. Can you note down, sir? I'll say by.
Yeah, tell me.
From input one resistor. For that one op amp. The second terminal will be the grounded, sir.
Oh, positive terminal is what?
That is negative terminal, sir. Upper part is a negative terminal. Minus and plus. For negative terminal, we have one resistor.
Okay.
For lower positive terminal, we have grounded.
Okay.
And from input only, from starting input, resistor below.
How much?
From there, we have another resistor, sir. From upper.
From input?
Below a resistor, yes, sir. Below resistor.
Okay.
One resistor. And for that, we have another op amp.
Here, another op amp is there?
Not that side, sir. Down one resistor, sir. After
Here.
resistor, second resistor.
Here, another op amp.
Yes, sir.
Okay.
The second, the positive op amp will be the grounded.
Okay.
And this third terminal will be the output, sir. Like.
This is output.
Yes, sir. And this will be attached to the output. Down one op amp will be attached to the output.
Okay.
Find V0 by Vi, sir.
Where is VI? This one is VI?
Yes, sir. That one is Vi. One resistor will be the 3 kilo. And another resistor will be 2 kilos, sir.
This is 3K and 2K.
Yes, sir. And the first 2K resistor after, and another resistor will be up from upper.
Here, another one.
Yes, sir. They connected to the output. And that 12 kilos, sir.
Okay.
What is the answer, sir? V0 by Vi. We need to find V0 by Vi.
Okay. Yeah. Now you tell me, if this is Vi, this node is also at Vi, no? This is at 0.
Yes, sir.
Then what should be the output here? This current is equal to this current minus R2 by R1 times of Vi. That's all.
This op amp will not be considered, sir.
Yeah, you consider. See, the KCL should not be violated. Entering equal to leaving, no?
Yes, sir. Entering is equal to leaving.
Leaving. So it is minus 12K by 2K into Vi. That's all. Now this op amp output also should be like that. How much is the op amp output? Minus 12K by 2K is minus 6 into Vi. minus 6 Vi, this op amp should also generate in this loop. Now what is happening here, I'll tell you. The same Vi is here, no?
Yes, sir.
The current drawn by this fellow is 0.
Yes, sir. Current is 0.
Because op amp draws no current. So the same Vi will come here, will appear here. So this structure is going to give some sort of negative feedback. We don't know.
Yes, sir.
So, so V0 will be this minus R2 by R1.
Yeah, okay. 6 volts, no, sir, answer?
Yeah, yeah. If Vi is 1 volt, yes.
Yeah, yeah.
Minus 6.
I got it, sir.
Yeah, yeah.
Thank you. That's it. That's it.
Okay. So shall we wind up? It's 10 o'clock. Yeah. Anybody else?
Sir, one more question, sir.
So
when we have the inverting amplifier is connected to the one matrix form, sir, like 1, 2, 1 dash and 2 dash.
Oh, I have to see that problem, no?
Okay, 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 sir.
Okay. Yeah.
Okay. Thank you, sir. That's
Yeah.
it.
Okay, then shall we wind up now for today? It's 10 o'clock.
Close this one.
Yeah. Thank you. Thank you all. Thank you for your patience. Good night.
Thank you, sir. Good night.
Yeah. Good night. Good night. వెంకట్ లాగౌట్ చేసేయి.
మీరు క్లోజ్ చేసేయండి సార్.
క్లోజ్ అంటే ఇక్కడ అంటే నేను నీకు మెయిల్ పంపించాలి కదా అందుకు.
మీరు మెయిల్ చేయండి ఏం కాదు.
ఇట్లే చేయొచ్చు కదా. మెయిల్ అని నిక్లాస్. వెంకట్ వెళ్ళిపోయింది. ఓకేనా?
Is your classes completed?
Yeah, I'm done.
Can I join yourself for half an hour?
Yeah, go ahead.
Yeah.